Hello there, and welcome to Life Beyond Seen, where curiosity drifts like a slow current and science finds room to breathe. Tonight, we're going somewhere few eyes have seen and even fewer minds have truly imagined. Somewhere that lies beneath storms, below sunlight, deeper than whales dare to sing. The Kuril Trench, a place so far down that it sits closer to the Earth's molten mantle than to the surface of the sea. Before we sink into this quiet abyss, I wonder, where in the world are you listening from tonight? Maybe you can hear rain outside. Maybe you're lying in bed. Maybe you can almost hear the low hum of the ocean through the walls. However far you are from the sea, the Pacific reaches you in ways you can't always see, in the air you breathe, in the weather that crosses continents, in the quiet pulse of tides that never stop moving. If you find this slow voyage through science and sleep soothing, I'd be grateful if you gave the video a like or shared it with someone who might need a calm moment too. It helps this little corner of curiosity stay afloat. Now, take a breath, loosen your thoughts, and imagine looking down into a stretch of ocean where sunlight has never reached, where even sound seems unsure how to travel. That's where we're going. The Kuril Trench lies off the coast of Japan and Russia's Kamchatka Peninsula, part of the Pacific Ring of Fire, the restless boundary where tectonic plates grind, buckle, and dive into the Earth's interior. It's a long scar in the planet's skin, running for nearly 1,800 kilometers, shaped by the slow-motion collision between the Pacific Plate and the Okhotsk Plate. To most of us, these are just names on a diagram, but down there, they're forces as old as continents. One plate slides beneath the other, dragging the seafloor down with it, forming a trench that drops more than 10 kilometers deep. That's taller than Mount Everest flipped upside down. Imagine standing at sea level and watching that mountain sink below you, all the way to its tip, and then some. That's how far the Kuril Trench reaches. It's easy to think of deep-sea trenches as voids, empty spaces at the edge of the map, but they're anything but. They're dynamic, violent, alive in ways that don't always include living things. The rocks themselves move, the sediments shift. Entire sections of the seafloor groan and buckle, creating earthquakes powerful enough to shake cities thousands of kilometers away. The 1952 Kamchatka earthquake, for instance, struck near this trench and sent waves racing across the Pacific. For the creatures that live there, quakes are just part of the weather, a tremor in the water that passes and fades. To us they're disasters, to them they're just Tuesday. The trench is not one uniform pit, but a chain of deep basins separated by ridges and faults. Cold, dense water from the surface sinks here, forming slow, heavy currents that slide along the bottom like invisible glaciers. It's dark, of course, but not silent. Even at these depths, microphones lowered into the Kuril Trench pick up a continuous symphony of low rumbles, distant echoes of quakes, the crackle of shifting sediment, and the faint crack of pressure building along faults. Some of those sounds are geological, some are biological, and some we still don't quite know. Humans first began to explore the trench properly in the mid-20th century, using heavy steel spheres lowered on cables, each one barely large enough for a person to sit in. These early bathyscaphs were little more than bubbles of air wrapped in steel, their windows tiny portholes of thick glass designed to resist the crushing pressure outside. At 10 kilometers down, the weight of the ocean above you is roughly 1,000 times that of the atmosphere. Every square inch of surface bears a ton of force. If a human body were exposed to that pressure unprotected, it would collapse instantly. And yet there are fish that live there, not by defying physics, but by quietly mastering it. Before we reach them, it's worth picturing what this world looks like. Light from the sun fades quickly in water, filtered and absorbed until all that remains by a few hundred meters down is a dim blue glow. Past a kilometer, even that vanishes. The Kuril Trench lies more than 10 times deeper. Down there, the darkness isn't just absence, it's substance, thick as velvet, absolute. You could shine a beam from the strongest flashlight ever built, and it would fade into blackness within meters. The water is near freezing, about 1 or 2 degrees above zero, and the pressure is so immense that even water behaves differently. It becomes slightly denser, slightly thicker. Metals creak, glass bends, electronics fail without extreme protection. Still, life persists. Not in defiance of the conditions, but because of them. Many deep-sea organisms are built not to fight their environment, but to become part of it. The fish known as the snailfish, for example, lives at depths where few others can survive. In 2022, researchers filmed one swimming near the bottom of the Kuril Kamchatka Trench, the deepest living fish ever recorded. It looked delicate, almost translucent, with fins like silk and skin as soft as jelly. Its body contains almost no air spaces, no swim bladder, no hollow bones. Every part of it is designed to resist collapse by avoiding anything that could be crushed. Its cells are filled with special molecules called osmolytes that prevent proteins from folding incorrectly under pressure. To the casual eye, it looks fragile. To physics, it's indestructible. Even smaller creatures thrive here in unimaginable numbers. Tiny amphipods, shrimp-like scavengers with transparent shells, scurry over the sediment like ghosts. They feed on marine snow, a constant drizzle of organic material falling from the upper ocean, bits of dead plankton, fecal pellets, fragments of jellyfish, and the occasional carcass of a larger animal that sank from the world above. Every speck is recycled. What we see as death at the surface becomes dinner in the deep. The rhythm of the abyss isn't about growth and decay in the way it is on land. It's about persistence, about making something out of almost nothing. Somewhere along the trench walls there are bacterial mats, vast pale fields of microbes feeding on chemicals that seep from cracks in the rock. These bacteria don't need sunlight or oxygen. They draw energy from reactions between water and minerals, creating food from the chemistry of stone. They form the base of a food web that stretches upward through worms, crustaceans, and finally to those ghostly fish. In the darkness, life forms its own ecosystem, complete and self-sufficient, powered not by the sun but by the Earth's own heat. Occasionally, when scientists lower remote cameras into the trench, they find strange shapes moving in the beam, long ribbon-like creatures that twist and vanish before the lens can focus, or pale discs that hover in the water like lost kites. Many of these are probably jellyfish or comb jellies, adapted to the deep, though some don't match any known species. It's easy to forget how little we've seen. The trench covers a larger area than many countries, and we've explored only tiny fragments of it, a few square meters here and there. Every descent reveals something new, sometimes a new species, sometimes a new question. There's a kind of quiet humility in realizing how much of the Earth remains unseen. We live in an age where we can send probes to other planets, map the moon in exquisite detail, and yet most of our own ocean floor is still a mystery. The Kuril Trench is one of the least accessible parts of that mystery, not because we lack curiosity, but because the cost of reaching it is immense. The pressure destroys equipment, the cold drains batteries, and the isolation means that if something breaks, there's no fixing it. Every expedition risks millions in technology and years of planning for a few hours of observation. Still, we go back. Because in that darkness lies not just the unknown, but the chance to see how life itself adapts to extremes. When we think of extreme environments, we often imagine heat, deserts, volcanoes, or space. But the abyss is its own kind of extremity, one of stillness, of weight, of silence. It challenges the idea that life needs abundance. Down here there's no sunlight, no plants, no seasons. The only constants are pressure and patience. To survive, organisms must become efficient to a level we can hardly comprehend. A deep-sea amphipod might live a decade on what a surface shrimp eats in a month. A snailfish might spawn only once a year, laying a few eggs in sheltered cracks, each one tended with more care than any coral reef nursery. The rhythms are slow, deliberate, unhurried. The abyss rewards persistence, not speed. The geology beneath them is anything but calm. Where the Pacific plate slides under the Okhotsk plate, magma wells up, melting rock and releasing plumes of heat. Sometimes, hydrothermal vents form even in these deep trenches, releasing superheated fluids rich in minerals. Around these vents, new forms of life appear, bacteria that feed on sulfur and methane, worms with blood-red plumes, tiny crustaceans clinging to the edges of the vents. The chemistry of these places is toxic by human standards, yet perfectly suited for those who evolved to breathe chemistry instead of air. It's strange to think that the bottom of this trench, a place we can barely visit, might resemble the early Earth more closely than anywhere on the surface today. Billions of years ago, before there was oxygen, before there were continents, life might have begun in environments like this, dark, hot, chemical, fed by the deep rather than the sun. Each time we send instruments into the Kuril Trench, we're not just exploring geography. We're looking backward in time, toward the possible origin of life itself. If you could stand, though you couldn't really stand, on the floor of the trench and look up, you'd see nothing but darkness. The idea of up would barely make sense. The water column above you would stretch for miles, a vertical ocean of weight and distance. The sounds of the surface, waves, rain, engines would never reach you. Instead, you might hear the faint crackle of distant rock shifting, the pop of gases escaping the sediment, and the slow, rhythmic movements of unseen creatures drifting past. To them, this is home. To us, it's an alien world. And yet, there's a thread that connects it to us. The deep sea plays a crucial role in the planet's systems. It stores heat, cycles carbon, and absorbs much of the excess energy we release into the atmosphere. The water that sinks in the Kuril Trench will eventually rise again thousands of years from now, somewhere far away, carrying with it traces of the present day. Every breath we take, every storm we feel is linked, however faintly, to these silent depths. For all its mystery, the trench is not isolated from the surface. Bits of plastic have been found even here, tiny fibres and fragments carried by currents, settling in the mud at 10,000 metres. Microbes are already colonising them. In a sense, humanity has visited every depth, even without meaning to. It's a sobering reminder that our reach extends further than our awareness, but it also shows how adaptable life is. Even our mistakes become new ecosystems. Exploring this trench means balancing awe with humility. We send machines that hum and click and glow, each one a tiny capsule of human curiosity wrapped in metal and data cables. They descend through layers of ocean where pressure increases by 100 atmospheres every kilometre, and still they function, capturing images, sampling sediments, recording sounds. When they rise again, they bring back more than specimens, they bring perspective. The reminder that Earth is still, in many ways, undiscovered. As we drift further along this descent, the line between life and landscape starts to blur. Creatures here don't stand out against their background. They are their background. Their colours match the sediment. Their movements are slow enough to seem geological. In a world without sunlight, visibility is a liability. The goal isn't to stand out, but to vanish, to merge with the water so completely that even predators can't tell where body ends and ocean begins. Everything about this place forces you to rethink what survival means. On the surface, we associate life with energy, movement, light, and speed. Down here, it's about endurance, subtlety, and balance. Nothing is wasted. Every chemical reaction, every movement, every breath is calculated by evolution to the smallest degree. Even death is efficient. A single whale carcass that falls into the trench can feed an entire ecosystem for decades. The bones become reefs, the flesh dissolves into nutrients and bacteria turn it into new life. The cycle closes perfectly, silently, without drama. The Kuril Trench is part of a system that circles the Pacific. The Mariana, the Tonga, the Japan trenches, all formed by the same relentless motion of tectonic plates. Together, they create a ring of deep scars that shape not only the ocean floor but the planet's climate and geology. Heat escapes through them. Carbon is buried in them. They are both the Earth's lungs and its scars, and among them, the Kuril remains one of the least explored, partly because of its location, partly because of its unpredictable weather, and partly because, in truth, few people even know it exists. It's not famous like the Mariana Trench, not romanticised in documentaries. It just is, a quiet depth doing what it has always done. And that's where we'll keep going next, into the slow architecture of this hidden world, where continents collide, sediments drift like slow snow, and the deep remembers every tremor. The story doesn't end here, it simply sinks a little deeper. When you think of the ocean, it's easy to imagine an endless blue plain stretching outward in all directions, a liquid desert with only surface waves and open water to define it. But the sea, especially the Pacific, isn't flat. It's an enormous, restless landscape, more varied and complex than the continents themselves. Beneath the surface lies a geography of impossible scale, a world of ridges, canyons, mountains taller than Everest, and valleys deeper than any we've ever walked. The Kuril Trench is part of that landscape, a single feature in a vast interconnected web of geological structures that shape the movement of oceans and the fate of continents. When we talk about the trench, we're really talking about the edge of the planet's living architecture. If you could drain the Pacific, the sight would be astonishing. Instead of smooth seabeds, you'd see towering mountain chains called mid-ocean ridges running like the spine of the Earth. You'd see deep scars where plates collide, and fields of volcanic cones that dot the ocean floor like constellations turned upside down. The Kuril Trench would appear as one of the darkest lines in this submerged map, a shadow curving northeast from Japan to Kamchatka, marking the border where one great slab of the planet's crust slides beneath another. It's here that the surface of the Earth folds back into itself. The process that creates trenches is called subduction. It's a slow, relentless movement that's been going on for billions of years, driven by the heat of the planet's interior. Beneath us, convection currents move through the mantle, like the slow boiling of stone. Hot rock rises, cools and sinks again, dragging entire continents along for the ride. Where two plates meet, one usually dives beneath the other, pulled downward by its own density. That's what happens at the Kuril Trench. The Pacific plate, heavy with ancient basalt and sediment, sinks under the lighter Okhotsk plate. As it descends, it drags down the edge of the seafloor, carving a trench that deepens as the plate moves. The angle of descent determines the trench's shape, steep here, shallower there, and controls everything from the types of earthquakes that occur to the kinds of volcanoes that form nearby. This motion is almost invisible to us, unfolding at a rate of only a few centimetres per year, about as fast as your fingernails grow. But over millions of years, that gentle crawl moves oceans and raises mountains. The Kuril Trench, as quiet as it seems, is one of the most active geological borders on Earth. Every few decades, it releases massive earthquakes, reminders that the planet's crust isn't a solid shell but a living, shifting skin. In a way, the trench breathes. It takes in old seafloor and exhales new land in the form of volcanic arcs. The Kuril Islands, strung like pearls above the trench, are the visible result of this invisible motion. Each island is the tip of a volcano built from the material that once lay far below the ocean floor. The architecture of this region isn't simple. It's a tangle of faults, ridges, and basins stacked like layers of a crumpled sheet. Imagine a line where two worlds meet, one descending, one resisting, and the immense pressure between them forcing rock to twist, fold, and fracture. The result is a structure that extends not just downward but sideways, a labyrinth of valleys and uplifts stretching for hundreds of kilometres. Sonar mapping has revealed steep walls lined with landslides, terraces carved by sediment flows, and ridges rising from the darkness like the remains of a drowned mountain range. Each one tells a story of collapse and renewal. The seafloor here is not static. Sediment from the continents flows into the trench through submarine canyons, carried by gravity and ocean currents. Sometimes these sediments slide down in vast avalanches called turbidity currents, rivers of mud and debris that race through the darkness faster than a jetliner, scouring the trench walls and reshaping the floor. These currents can be triggered by earthquakes or volcanic eruptions, and they carry with them everything from microscopic plankton shells to boulders the size of houses. When they finally settle, they leave behind layered deposits that scientists can read like tree rings. Each layer is a record of the ocean's history, a snapshot of what was happening above when it fell. The trench isn't just a geological sink, it's also a conveyor belt, a place where matter disappears from the surface world and re-enters the planet's interior. As the Pacific plate sinks, it carries with it sediments rich in carbon, calcium, and organic material, remnants of life that once floated near the surface. Deep within the mantle, these materials are transformed, melted, and eventually rise again through volcanic eruptions. It's a cycle that links the deep sea to the sky. The carbon released by volcanoes today might once have been a shell drifting through the water millions of years ago. Every breath of volcanic gas is, in a sense, the exhalation of ancient plankton. When we think of architecture, we think of design, purpose, intention. But the Earth's architecture isn't built to plan. It emerges from pressure and time, and yet there's an elegance to it, a balance between destruction and creation that sustains the planet's long-term stability. The Kuril Trench is one of the key places where that balance plays out. Without subduction zones like it, the Earth's surface would have long ago become overloaded with crust, mountains would pile endlessly upward, and volcanic activity would fade. It's the recycling system that keeps the world geologically alive. To study this architecture, scientists use a combination of techniques that sound almost like magic. They send sound waves into the ocean and measure how they bounce back, creating sonar maps that reveal the shape of the seafloor. They use seismic sensors to detect how waves from earthquakes travel through rock, allowing them to reconstruct what lies miles below. They drop autonomous robots, tethered submersibles, and weighted probes that collect cores of mud from the bottom, each core a vertical time capsule that can tell stories spanning thousands of years. Every discovery adds a new line to the blueprint of the deep. One of the most remarkable things about the Kuril Trench's structure is how it changes with depth. Near the surface, the walls are steep and fractured, scarred by landslides. Farther down, the slopes become smoother, covered by fine sediments that have drifted down over millennia. At the very bottom lies the Hadal Zone, named after Hades, the Greek underworld. It's a narrow world, existing only in deep trenches, where pressure exceeds 1,000 atmospheres. The shape of the trench determines how water moves through it. In some places, cold, oxygen-rich water sinks, bringing with it nutrients that feed microbial life. In others, stagnant layers form, isolating pockets of chemical reactions that could not occur anywhere else. The architecture of the trench is not just physical. It shapes ecosystems, guiding how life can exist and where. In this sense, the Kuril Trench is both a boundary and a bridge. It divides tectonic plates but connects biological and geological cycles. The same forces that trigger earthquakes also feed the microorganisms that thrive on chemical energy. The same sediments that slide into darkness carry the building blocks of life. Even the shape of the trench affects what survives there. Deep crevices provide shelter from currents. Smoother slopes allow nutrients to settle. If the trench were even slightly different in angle or depth, the species that live there might not exist at all. Evolution, it seems, designs itself around geology. One of the most fascinating features along the trench is what scientists call the outer rise, a bulge in the seafloor that forms just before the plate bends downward into the subduction zone. It's here that the oceanic crust begins to crack under tension, releasing small earthquakes long before the plate finally dives. These cracks become conduits for fluids, water forced down through fractures, reacting with minerals and carrying dissolved elements back up. This process alters the chemistry of the crust, creating zones rich in serpentine and other unusual rocks. For biologists, these cracks are highways of life, feeding energy into the deep through chemical gradients. For geologists, they're the first step in recycling the planet. The Kuril Trench also plays a quiet role in regulating global climate. By dragging sediments and carbon into the mantle, it acts as a long-term sink for greenhouse gases. It's a process that unfolds over millions of years, invisible on human timescales, but essential for maintaining the balance of the atmosphere. Without it, the planet might swing between extremes of heat and cold, its climate far less stable than the one we know. In this way, the trench, unseen and silent, helps keep the world habitable. It's strange to think that the stability of the air above our heads depends on the slow drowning of seafloor thousands of kilometers away. Some of the most haunting discoveries about this architecture come from sound rather than sight. When hydrophones were placed along the trench, they recorded a constant background hum, low-frequency vibrations caused by the movement of water and rock. Occasionally there are sharper bursts, the echoes of distant quakes or submarine landslides, but sometimes, amid the geological noise, there are sounds that don't quite fit. Rhythmic pulses, repeating clicks, long, drawn-out moans that seem organic but don't match any known species. Scientists are cautious about assigning meaning to them, but it's hard not to wonder. The architecture of the trench may shape not only the flow of water, but the very language of the deep. There's another kind of architecture hidden here too, the human one. Along the trench, arrays of cables and instruments stretch across the seafloor, part of international efforts to monitor earthquakes and tsunamis. Some of these sensors have been in place for decades, transmitting data through fibre optic lines buried in mud. They form a network of artificial nerves, listening for the planet's heartbeat. When a quake strikes, the signals travel faster than the waves themselves, allowing warnings to reach coastal cities in time to save lives. In that sense, our technology has joined the architecture of the trench, a small but vital part of its living system. It's humbling to realise that what we call the deep sea's architecture is also a record of time. Each layer of sediment, each fold in the rock, each ridge and fracture tells a story that stretches back millions of years. It's not just space that defines this place, it's history written in pressure and depth. The Kuril Trench is older than civilization, older than the species listening to this story, yet it's not a relic. It's still moving, still changing, still sculpting the future shape of the Pacific. If you could speed up time and watch this region evolve over eons, it would look alive. Mountains would rise and crumble, islands would appear and vanish, volcanoes would ignite along invisible lines. The trench would deepen and shift, consuming ocean floor and creating new crust elsewhere. What seems eternal in the moment is always temporary in the scale of the Earth. Even the deepest abyss is just one phase in a long cycle of renewal. The architecture of the sea isn't built to last forever, it's built to change. And through that slow, unending change, life continues to adapt. Microbes evolve to feed on new minerals exposed by fresh fractures. Fish move deeper or shallower depending on the slope. Even the chemical composition of the water shifts as rocks dissolve and react. It's a constant conversation between geology and biology, each shaping the other. The Kuril Trench isn't just a structure, it's a living dialogue between rock, water and life. As we keep descending through this hidden architecture, the details grow finer, the patterns more intricate. The trench narrows, pressure mounts, and the familiar rules of the ocean give way to something stranger. The environment becomes less about gravity and more about chemistry, less about currents and more about gradients. The sea's architecture transitions from the physical to the biological, from rock to tissue, from the skeleton of the planet to the bodies that inhabit it. The deeper we go, the more the line between architecture and organism dissolves. Tube worms build chimneys of minerals that resemble cathedrals. Bacteria form mats that look like marble veils. Even the smallest crustaceans carve burrows and tunnels into the sediment, shaping micro-landscapes that last for centuries. The sea builds, and life decorates. Together they create a world that, though unseen, rivals any coral reef in complexity. And that's where we drift next, further into the darkness where continents collide, where the pressure thickens the water itself, and where life begins to appear not as a visitor, but as a resident sculptor. The structures grow stranger, the organisms more alien, and the question becomes not just how they survive, but how the deep has become their home. As the slow descent continues, the surrounding water begins to feel heavier, though weight here is more a presence than a pressure. The deeper you go, the more the world above fades, and what replaces it is not emptiness, but a dense, invisible field of forces. This is where continents collide and oceans tremble, where the hard skin of the earth folds inward and the sea itself becomes an accomplice in the planet's constant rebalancing act. The Kuril Trench, for all its quiet appearance, is a fault line not only between plates of rock, but between stability and chaos. When people imagine earthquakes, they picture the ground shaking underfoot, buildings swaying, and the sound of glass rattling in window frames. But the true violence of most quakes begins far from view, down in these hidden seams of the planet. The collision of the Pacific and Okhotsk plates is not an event, it's a condition, a permanent state of tension. The Pacific plate is pulled westward, descending into the mantle, while the smaller Okhotsk plate resists and bends. Over centuries, the strain builds invisibly until it overcomes friction, releasing a burst of energy that moves through rock like a shock wave through steel. Up above, the ocean responds, lifting and dropping in enormous sheets of water that can travel across the entire Pacific basin. Every tremor that starts here reshapes the world in ways both immediate and slow. The 1952 Kamchatka earthquake, for instance, registered as one of the largest ever recorded with a magnitude of 9.0. The seafloor rose and fell by meters in seconds, displacing billions of tons of water and sending tsunamis toward Alaska, Hawaii, and even Chile. The energy released in that single event was equivalent to several thousand atomic bombs. Yet when it happened, the surface gave no warning. The water merely swelled, hesitated, and then began to move. To the life in the trench, it was another pulse in an endless rhythm. To humans, it was a reminder that the solid ground we trust is never truly still. These collisions between plates are part of what's called the subduction cycle. As one plate sinks, it drags down sediments, water, and minerals from the ocean floor. When these materials reach depths of around 100 kilometers, the heat and pressure squeeze the water out of the rocks. That released fluid rises into the overlying mantle, lowering its melting point and triggering the formation of magma. That magma, lighter than the surrounding rock, begins to ascend, sometimes feeding volcanic arcs like the Kuril Islands or Japan itself. So, when continents collide, they don't just create earthquakes, they give birth to volcanoes. The trench is the inhale, the volcano the exhale. Together they are one system, moving matter from the surface to the deep and back again in a cycle older than the seas themselves. It's strange to think that the very mountains we see above water are the mirror image of these unseen trenches. One rises because the other sinks. The Himalayas exist because somewhere else the seafloor disappears. In that sense, every collision is both destructive and creative. The Kuril Trench consumes, but its shadow above, the Kuril-Kamchatka volcanic arc, builds. The islands there form a jagged line of peaks and craters stretching hundreds of kilometres, some still active, their eruptions punctuating the region's long silences. When one erupts, ash falls into the ocean, adding new minerals that drift down into the trench, feeding the deep ecosystems below. What begins in the collision of continents ends in the nourishment of life at the bottom of the sea. The tremors that ripple through the trench don't all announce themselves with violence. Some are slow earthquakes, events that unfold over days or weeks, too gradual to be felt at the surface but powerful enough to move continents by centimetres. These silent shifts are recorded only by the sensitive seismometers buried in the sea floor. They reveal that the trench is always in motion, never truly at rest. The ocean floor creeps, slips, and adjusts like an enormous living joint, flexing under the weight of the planet. The phrase, continental drift, hardly captures the intimacy of this motion. It's not drifting so much as breathing, an expansion and contraction that plays out over millions of years. Beneath the visible layers, the contact zone between the plates, the subduction interface, is one of the most complex environments on Earth. Here, rock behaves in ways that defy simple categories. Under extreme pressure and temperature, solid rock can flow like clay, while fluids trapped between layers act as lubricants, altering how easily the plates slide past one another. Tiny earthquakes, sometimes called microseisms, pop and snap continuously, like the sound of ice settling on a frozen lake. Each one releases a trace of energy, a note in the long symphony of tectonic motion. Over time, these microevents shape the stress patterns that determine where the next major quake will occur. The interface is also where some of the most unusual chemistry on the planet takes place. As the subducting plate descends, it carries not only sediments, but also trapped seawater locked in the minerals of the crust. This water contains dissolved salts, gases, and organic compounds. When the rock heats up, these fluids are expelled, rising through fractures in the overlying plate. Along the way, they react with the surrounding minerals, forming serpentine, talc, and other metamorphic rocks. The result is a patchwork of materials, each with different densities and strengths. In some places, these variations create barriers that lock the plates together for centuries, storing potential energy. In others, they allow slow, steady slip. The trench is a map of stress, pressure, and release, an ever-changing balance of locked and free zones. Scientists have drilled into the upper parts of such subduction zones to retrieve cores of rock and sediment, though the Kuril Trench itself remains largely untouched by direct drilling due to its depth and instability. What we've learned from other trenches, like the Japan or Nankai trenches, gives a sense of what might lie here. Layers of compacted clay, volcanic ash, and fine silt alternate with harder slabs of basalt, each layer folded and twisted like a shuffled deck of cards. Tiny fossils in these layers tell us when each was deposited. Some come from warm, shallow seas that existed millions of years ago, others from cold glacial waters. Each one is a timestamp, a marker of shifting climates and continents. The Kuril Trench holds these records in perfect darkness, an archive of the Earth's restless history. Above this zone of slow violence, life continues with a kind of detached indifference. The creatures that inhabit these depths experience earthquakes differently than we do. To them, the shockwaves are merely oscillations in pressure, a passing distortion in an already unstable environment. Some animals even use these vibrations to navigate or locate prey. Sensors have detected that deep-sea fish and crustaceans sometimes move en masse just before a quake, as if sensing the build-up of tension in the rocks below. It's not clairvoyance, it's sensitivity. Evolution has taught them to read the Earth's moods. Every time the plates grind and shift, the seafloor changes shape. Ridges rise, valleys deepen, and sediments slide down the slopes in massive underwater landslides called slumps. These slumps can release clouds of debris that drift for miles, burying habitats and then, slowly, becoming habitats themselves. Bacteria colonize the fresh surfaces. Amphipods burrow into the new layers. Life doesn't flee from disturbance, it reorganizes around it. In the deep sea, survival isn't about avoiding catastrophe, it's about adapting to it. The Kuril Trench is a masterclass in that principle. One might imagine that with all this movement and destruction, the trench would be a chaotic mess, yet it's anything but. There's an order in the seeming disorder, a rhythm to the quakes and flows. Scientists have noticed that major earthquakes in this region often follow patterns, with certain segments of the trench releasing their strain in sequence over decades. It's as if the fault line passes the energy along, one section at a time. This sequence, called a seismic cascade, has been traced along the Kuril-Kamchatka arc for more than a century. It doesn't make prediction possible, not yet, but it hints that the Earth too operates in cycles. Even the quiet periods between quakes are full of movement. The subducting plate, as it descends, scrapes against the overlying crust, creating small folds and ridges that ripple outward. These ripples shape how sediments settle, guiding deep currents and influencing where nutrients collect. It's a subtle but crucial link. The movement of continents controls the flow of microscopic life. In this way, geology and biology are entangled not just through time but through daily existence. The rhythm of earthquakes determines where food gathers and where creatures can live. When researchers map this collision zone using sonar and seismography, they see more than just a line on a chart. They see a living topography, an undulating dynamic landscape sculpted by stress and gravity. The trench's floor is punctuated by small hills called horsts and depressions called grabens, created by the stretching and compression of the crust. These features rise and fall over centuries, creating miniature worlds within the larger abyss. Some of these ridges are coated with manganese nodules, slow-growing metallic concretions that form over millions of years as minerals precipitate from seawater. Others are covered with fine silt, smooth and untouched, until the next quake resets them. To explore such a place is to confront time in a physical form. A single centimetre of sediment might represent 1,000 years. A landslide can bury a million-year-old layer in minutes. The Kuril Trench compresses geological time into visible form, a kind of clock that ticks not in seconds but in strata. And while we measure our lives in hours and days, here, the Earth measures its own in movements and layers. Every quake, every tremor, every grain of sand settling on the seafloor is part of that ongoing measure. There's a quiet irony in how the planet's most violent processes can give rise to such calm landscapes. If you could hover above the trench in a submersible, you'd see smooth plains of sediment stretching into darkness, interrupted only by the occasional ridge or crack. The violence that shapes them is invisible, stored as potential energy deep within the rocks. The ocean absorbs it, diffuses it, hides it. Only when that balance is broken does the power reveal itself briefly before vanishing again into stillness. These collisions have another more distant consequence. They shape the distribution of entire ecosystems across the Pacific. Volcanic arcs formed by subduction release minerals like iron, which eventually wash into the ocean and fertilize plankton blooms. Those blooms feed fish, which feed larger animals, and in time, some of that organic matter sinks back into the trench. Even whales, when they die and drift downward, become part of this exchange. Their bones settle on slopes created by ancient quakes, their decay releasing nutrients that spark new colonies of life. In a roundabout way, the trembling of continents sustains the quietest corners of the ocean. What we call disaster is, to the planet, maintenance. The Kuril Trench is one of the gears in that mechanism. It resets stress, recycles matter, and renews surfaces. Without such collisions, the Earth would stagnate, its interior heat trapped, its atmosphere unbalanced, its crust unchanging. Our world's beauty, the mountains, valleys and oceans, exists because the planet refuses to stay still. The trembling of the Kuril Trench is not a flaw. It's the heartbeat of the Earth itself. The human presence in this story is faint but growing. Instruments now line parts of the trench, listening for shifts in pressure, measuring ground motion, and tracking the slow warping of the seafloor. Satellites above register tiny displacements in the land after each quake, mere millimeters of movement that reveal where strain is building next. This network of observation is our way of eavesdropping on the conversation between continents. The more we listen, the clearer the rhythm becomes, though it remains a language we don't yet fully understand. Even so, the lessons are tangible. Understanding how and where the Earth trembles has saved lives, improved building designs, and deepened our sense of connection to the forces that built the world. The Kuril Trench reminds us that the planet is not a stage set for our comfort, but a dynamic system that continues to evolve. We live atop moving plates, above shifting trenches, beside restless arcs of fire. And yet, despite that fragility, life thrives. Perhaps it thrives because of it. As we drift deeper into this borderland between plates, the pressure increases, the temperature drops, and the water grows stiller. The light from our instruments fades into a haze of particles drifting like dust in a dark room. Somewhere below, the two plates continue their slow collision, shaping the future in silence. This is not an ending or a beginning. It's just another moment in the long conversation between ocean and continent, between motion and rest. The trembling continues, and within that motion, life endures. And further below that trembling skin, deeper still, lies a region so silent it borders on otherworldly, a place where sunlight has never existed, where chemistry replaces photosynthesis, and where the very idea of life must be redefined. That is where we're going next, into the depths where light fades, pressure rises, and silence deepens. As the descent continues, the faintest traces of daylight begin to vanish, absorbed by the ocean itself. What was once blue becomes a darker blue, then navy, then the colour of old ink, until even that disappears. The human eye is built for sunlight, for reflection and contrast, but down here there is no reflection and almost no contrast. Shapes fade into gradients, edges blur, and before long the concept of seeing starts to lose meaning. In the upper ocean, light defines life. In the abyss, its absence does. The Kuril Trench lies within that absolute absence, a world ruled not by sight but by touch, vibration, and chemistry. It takes less than 1,000 meters for the last photons from the sun to disappear completely. Everything below that is night, a night so total that it's been undisturbed for millions of years. The water here is cold, barely above freezing, and yet it never freezes, not because of warmth, but because of pressure. With each 100 meters, the weight of the ocean above adds another 10 atmospheres of force. By the time you reach the depths of the Kuril Trench, the pressure is over 1,000 times greater than what you feel at the surface. It's a kind of weight that's impossible to imagine, not because it crushes, but because it's everywhere, pressing equally on every direction. To survive here, organisms must not resist that pressure but become part of it. This is where the surface world and the deep world diverge entirely. Above, energy comes from the sun, filtered through photosynthesis into plants, algae, and everything that eats them. Below, energy comes from what drifts down from above, or what seeps out of the planet itself. Every flake of dead plankton, every scrap of organic matter, every piece of detritus becomes a lifeline. Scientists call this constant drizzle marine snow. It falls gently through the water column, glowing faintly under the right light, a steady rain of decay that never ends. To us it might sound bleak, but for the creatures of the deep it's abundance, a perpetual meal delivered from a world they'll never see. Marine snow doesn't fall evenly. Currents carry it sideways, eddies twist it into spirals, and in some regions, like the trench slopes, it gathers in dense layers. When researchers send sediment traps into the Kuril Trench, they collect thousands of particles per square metre each day, most smaller than a grain of sand. Each one carries within it carbon, nitrogen and minerals, the building blocks of life. Together they create a slow-motion ecosystem where everything depends on patience. A single piece of food may take months to sink from the surface to the bottom, but down here there's no hurry. The deep sea runs on a different clock. As light fades, so does colour. The pigments that once mattered, reds, oranges, greens, become useless. Many deep-sea species lose their colour entirely, turning transparent or pale white. Others evolve pigments that absorb the faint traces of blue light that still penetrate from above, giving them a spectral shimmer visible only to themselves. But the most striking adaptation is not the loss of light, but the invention of new light. Bioluminescence becomes the currency of communication. Tiny flashes from plankton, pulses from jellyfish, slow glows from deep-sea fish, all of them speak in patterns of light. It's a silent language written in chemistry, not sound. To create bioluminescence, organisms use a molecule called luciferin, which reacts with oxygen in the presence of an enzyme, releasing energy as light. In the upper ocean, this serves as camouflage or distraction. In the abyss, it's more than that. It's the only visible form of existence. Imagine being in a place where the only illumination comes from living things. Each flash and glow is a heartbeat, a signal that says, "I am here." Some use it to attract mates, others use it to lure prey. Still others, like certain squid and crustaceans, use it defensively, releasing clouds of light the way surface animals release ink. The darkness isn't empty. It's filled with these brief, flickering lives. But in the Kuril Trench, bioluminescence becomes rarer the deeper you go. Below 6,000 metres, most light-producing species vanish. There's no evolutionary advantage to glowing when almost no one is there to see it. The world becomes not just dark, but invisible. Sight itself becomes optional. Many fish down here have eyes that are reduced to small black dots, or none at all. Instead, they've evolved sensory systems that can detect pressure changes, electrical fields, and chemical gradients. Some can sense movement through their lateral lines, long canals filled with fluid that detect vibrations. Others rely on taste and smell, which in the absence of light can travel astonishing distances through the water. Sound behaves differently here too. In the deep sea, it travels faster and farther because of the density of the water. A single low-frequency vibration from a landslide or whale call can carry for hundreds of kilometres. Hydrophones placed near the Kuril Trench record a soundscape unlike anything on land. There's the constant hiss of distant currents, the faint crackle of micro-bubbles collapsing, and every so often the deep rumble of the earth shifting beneath. Then there are sounds that defy easy classification. Pulses, knocks, tones, some from known species, others from something else entirely. The deep ocean is full of noises we don't yet recognise, each one a reminder that we've barely begun to listen. The silence of the trench is not the silence of emptiness, but of scale. It's not that nothing happens here, it's that everything happens slowly. Even chemical reactions take longer because of the cold. Decomposition is sluggish. Movement is deliberate. A fish may hover for hours in one place, conserving energy, waiting for a meal that might not come for days. A worm may spend its entire life in a patch of sediment no larger than your hand. Down here, the boundaries of survival are tight. Every joule of energy counts. Every action has a cost. The creatures that thrive are those that have learned to live with almost nothing. Pressure defines everything. At these depths, gases behave differently, proteins fold in unfamiliar ways, and membranes must be reinforced without becoming brittle. Most animals that live here have gelatinous bodies with few rigid structures. Their flesh is soft, their bones thin or absent, their organs surrounded by water of nearly equal density. This prevents collapse under immense pressure. Inside their cells, specialized molecules, piezolates, protect vital enzymes from being distorted. Without these chemical adaptations, life would simply disintegrate. What's remarkable is how normal this all becomes at the right scale. For the snailfish gliding just above the trench floor, this crushing weight isn't a burden. It's home. If a human-made submersible were to descend into the Kuril trench, its structure would creak continuously as it adjusted to the pressure. The hull would compress by several centimetres, and every piece of metal would be under constant strain. Communication with the surface would lag. Light from the vessel's lamps would scatter into a mist of particles, and visibility would shrink to only a few meters. The outside temperature would hover around 2 degrees Celsius, while the water's density would make movement feel sluggish, almost syrupy. Even the simplest maneuver, turning, rising, adjusting positions, would require power and precision. Down here, the ocean doesn't forgive errors. Yet amid this mechanical fragility, life continues effortlessly. Amphipods drift through the water like tiny ghosts, their translucent bodies pulsing with faint movements. Holothurians, sea cucumbers adapted to the deep, crawl across the sediment, ingesting and filtering it grain by grain. Some of them have evolved to float, inflating their bodies like balloons to drift between feeding grounds. Starfish too make their home here, their limbs moving so slowly they seem motionless. At this depth, every organism has adapted not to speed or competition, but to endurance. Survival is less about outpacing others and more about lasting long enough to reproduce once. What's fascinating is that many of these creatures are found only in deep trenches. Scientists call them huddle endemics, species that evolved specifically for this environment and nowhere else. The isolation of trenches, separated by thousands of kilometers of shallower sea floor, creates evolutionary islands. Each trench becomes a world with its own unique residents. In the Kuril Trench, researchers have identified snailfish species, amphipods, and worms that exist nowhere else on Earth. Their DNA shows how evolution adapts in parallel to the same pressures in different corners of the ocean, an echo of survival repeated in darkness. Even microbes play their part in this architecture of endurance. Samples of sediment from the trench reveal vast communities of bacteria and archaea that feed on compounds like methane, ammonia, and hydrogen sulfide. These microbes form the foundation of life here, converting chemical energy into organic matter that sustains higher organisms. Some of them live inside rocks, others form mats on the seafloor. Many remain dormant for years, waiting for a rare influx of nutrients, perhaps a dead fish, perhaps the remains of a whale drifting down from the light. When that happens, the entire ecosystem awakens. Amphipods gather, bacteria multiply, worms appear from the sediment. In days, the carcass is stripped clean, its nutrients reabsorbed into the slow metabolism of the deep. The trench walls themselves are habitats, where cracks open, small colonies of life gather around mineral-rich seeps. These aren't the dramatic hydrothermal vents found in mid-ocean ridges, but quieter, colder flows of fluid that seep from the rock. They carry dissolved methane and sulfides that feed specialized microbes. Those microbes, in turn, attract small crustaceans and worms, forming miniature oases in the desert of the deep. It's easy to think of the trench floor as flat and featureless, but in reality it's patchy, a mosaic of activity surrounded by vast calm. Life here is concentrated in pockets, each one a flicker of vitality amid the stillness. If you were to hover near one of these seeps and watch closely, you'd see interactions that seem almost choreographed. An amphipod scuttles in, disturbed by a slow-moving worm. A cluster of translucent shrimp pulses in the current, their antennae sweeping for particles. Tiny white crabs patrol the edges, feeding on whatever drifts their way. It's a small, self-contained system, elegant in its simplicity. The energy that fuels it might come from deep within the earth, or from the slow rain above, but the result is the same: persistence. What's perhaps most humbling about this world is that, in many ways, it functions independently of ours. The deep ocean is not an extension of the surface, but a parallel existence. Its rhythms don't match our seasons, its inhabitants don't follow our cycles. They exist on geological time, where centuries can pass with little change, and yet the boundary between the two worlds is porous. When storms rage on the surface, turbulence can carry organic matter downward. When volcanoes erupt, ash falls into the sea and drifts down like snow. Even distant human activity leaves traces here. Tiny plastic fibres, chemical residues, microscopic metal particles. The abyss is far, but it's not separate. Silence in this environment is not the absence of sound, but the absence of interruption. Everything that happens here is part of a continuum. The slow settling of particles, the faint current against the trench wall, the almost imperceptible stirring of a fish's fins, all merge into a kind of constant, low-frequency hum. When humans listen to recordings from the deep, they often describe the sound as soothing, almost hypnotic. It's as if the ocean itself is breathing. To understand the abyss is to confront how limited our senses are. We rely on light and air to navigate our world, but in this realm, neither applies. Machines help us translate it. Cameras, sensors, hydrophones. But even they capture only fragments. The rest must be imagined, pieced together from data, inference, and the faint traces left on instruments. It's an odd partnership between knowledge and wonder. We can measure temperature to the thousandth of a degree, yet we still don't know what many of these animals look like alive. The deeper we go, the more precise our instruments become, and the less certain our understanding feels. Pressure, darkness, silence. These are not just conditions here, they are constants, woven into every molecule of life. The trench is not a place of despair or danger. It's a demonstration of balance, of what happens when organisms evolve not to fight the environment, but to harmonize with it completely. Each species, from the smallest microbe to the largest snailfish, is a note in that harmony. And together, they compose a world that exists in perfect quiet, far from the noise of waves and wind. If you linger in that thought long enough, the boundary between observer and environment starts to dissolve. The stillness seeps in, the weight settles around you, and the concept of time stretches thin. You realize that the deep sea doesn't rush, doesn't hurry, doesn't even flow in the way rivers do. It endures, it holds, it waits, and in that waiting, it sustains life that seems impossible. As we keep descending along the trench walls, through this dark equilibrium of pressure and silence, a faint realization takes hold. This is not the bottom yet. The world still extends downward, deeper than any submersible has gone here, into regions where even the instruments struggle to function. Somewhere below, there are still layers of sediment untouched, species unseen, and processes we can only guess at. The pressure continues to rise, the light continues to fade, and the silence somehow grows deeper still. And just below that threshold, in places where even the strongest light can't reach, and only the faint hum of the earth remains, life begins to transform into something stranger, something that doesn't resemble what we think of as familiar at all. That's where we're heading next, into the world without sunlight, where existence is written not in colour or warmth, but in chemistry and persistence. The point where light ceases to exist marks more than a boundary between brightness and darkness. It's the edge of everything familiar, the point where the ocean becomes self-contained, where energy no longer comes from above but from within. Here begins the world without sunlight, a realm that has never seen morning or evening, a place where time moves not by the rising of the sun, but by the slow drift of particles and the quiet rearrangement of molecules. The Kuril Trench lies deep inside this perpetual night, and to enter it is to witness how life can find a way when light itself has long been forgotten. When scientists speak of life, they almost always begin with the sun. The warmth, the radiation, the photosynthetic engines that transform light into sugar, the chains of energy that link leaf to insect, insect to bird, bird to predator. But in this world, that system doesn't apply. Down here, sunlight is a rumour, and photosynthesis is an ancient legend. Every gram of living tissue, every flicker of movement, every breath taken in the abyss depends either on what falls from above or what seeps up from below. The first is the rain of organic debris, marine snow and the occasional carcass. The second, far rarer but more potent, is the energy that emerges from the Earth's crust. It's easy to assume that without sunlight there can be no colour, no movement, no beauty. But the world without light has its own kind of detail. The creatures that live here have evolved shapes that look less like animals and more like ideas sculpted by necessity. Their bodies are simplified, stripped of anything unnecessary. The snailfish that glides above the trench floor has no scales, no swim bladder, and almost no bones. It moves with slow undulations, more like a ribbon than a vertebrate. Its skin is translucent, revealing faint traces of muscle and organs beneath. The softness isn't fragility, it's efficiency. At these pressures, strength lies not in resistance, but in yielding. Nearby, amphipods scurry across the sediment, their exoskeletons thin and glassy. They are scavengers, feeding on the remains of whatever drifts down. When a whale dies far above, its body sinks slowly, twisting in the currents until it reaches the bottom. What happens next is one of the most extraordinary ecological processes on Earth. Within hours of its arrival, the first wave of scavengers descends, sharks in shallower regions, but in the trench, amphipods, worms and bacteria take their place. They strip the flesh, consume the fat, and reduce the carcass to bones. Then, other species arrive, specialized microbes that feed on the lipids within the bones themselves, producing hydrogen sulfide as a byproduct. That chemical, toxic to most life, becomes food for other bacteria, which in turn feed new layers of worms and crustaceans. What begins as death becomes an explosion of life. A whalefall can support a community for decades. Such communities are rare, but they reveal the rule that governs this world. Nothing is wasted. Every molecule of carbon, every fragment of protein, every atom of nitrogen is recycled again and again. The absence of sunlight doesn't mean the absence of energy, it means energy is more precious. The food web here is compact, efficient, and deeply interconnected. A single gram of sediment may contain millions of microorganisms, each one breaking down complex molecules into simpler ones, feeding others in turn. There is no surplus, no luxury, no waste. The world above burns through energy like a wildfire. The world below spends it like a miser counting coins. This efficiency extends to the way organisms reproduce and grow. Many deep-sea species mature slowly, sometimes taking years to reach adulthood. Some reproduce only once, releasing small numbers of well-developed offspring that have a higher chance of survival. Others clone themselves, budding off identical copies when conditions are favourable. Because food is unpredictable, their strategies must be flexible. If a sudden influx of nutrients arrives, a dead squid, a cascade of organic matter, they multiply quickly. When scarcity returns, they retreat into dormancy, conserving every possible resource. Life here is less about progress than persistence. Temperature plays a quiet role in this equilibrium. The water at the bottom of the Kuril Trench is a uniform 1 to 2 degrees Celsius. It never changes, not in summer or winter, not over centuries. This stability might sound comforting, but it also limits metabolism. Chemical reactions slow down, movement becomes costly, and growth nearly stops. Yet for some species, that slowness is an advantage. It reduces the need for energy, allowing them to survive for astonishing lengths of time. Some deep-sea clams and sponges are thought to live for hundreds, perhaps thousands of years. Their existence is measured not in seasons, but in eras. The absence of sunlight has turned time itself into a luxury. The trench floor is a landscape sculpted by motion, yet appearing still. Fine sediment blankets everything, settled from millennia of slow rain. In some areas it forms ripples shaped by faint bottom currents. In others, it lies flat and unbroken, smooth as powdered glass. Small hills mark places where debris has fallen from the trench walls, and cracks reveal streaks of darker material where fluids seep upward. When robotic cameras glide over these plains, they capture what looks like stillness, but it's deceptive. Bacteria are active within the sediment, processing chemicals, exhaling gases, and forming invisible mats just below the surface. If you could magnify the view 1,000-fold, you'd see movement everywhere. Microscopic organisms wriggling through tiny grains of sand, threads of fungi-like bacteria reaching towards sources of nutrients, cells dividing quietly in the dark. The world without sunlight is far from dead. It's simply running on a slower rhythm. One of the most intriguing forms of life found here is the piezophile, a term that means pressure-loving. These are microorganisms specifically adapted to high-pressure environments. Their enzymes, cell membranes, and genetic structures function best at pressures that would crush most life. Some piezophiles can't survive if brought to the surface. They literally fall apart in low pressure. Their biology is tuned to the deep, a testament to how adaptable life can be. Studying them has led to unexpected insights into biochemistry. Enzymes from these microbes have proven valuable in research and biotechnology, helping scientists understand how molecules behave under extreme conditions. In a way, these invisible organisms from the Kuril Trench have contributed to discoveries that reach far beyond the ocean. Where light cannot penetrate, chemistry becomes the foundation of existence. Chemosynthesis, the process by which certain microbes convert chemical energy into organic matter, replaces photosynthesis as the base of the food chain. In the Kuril Trench, these chemosynthetic communities are found near cold seeps, where methane and hydrogen sulfide emerge from the sediment. The bacteria that live there use these compounds the way plants use sunlight, producing carbohydrates that sustain entire ecosystems. Worms, clams, and crustaceans cluster around these seeps, living symbiotically with the microbes inside their bodies. It's an arrangement as elegant as any coral reef, just hidden beneath a layer of darkness and silence. This kind of life independent of sunlight, has profound implications. It suggests that biology isn't limited to the narrow band of conditions we experience at the surface. It can thrive wherever there's a source of energy, even if that energy comes from rocks instead of rays. The discovery of these deep-sea ecosystems in places like the Kuril Trench changed our understanding of life's boundaries. It showed that the spark of existence doesn't require sunlight, air, or even warmth. It needs only the right chemistry and enough time. That realization has reshaped how we search for life beyond Earth, guiding missions to icy moons like Europa and Enceladus, where oceans may exist beneath frozen crusts, sustained not by stars but by the heat of planetary cores. In a sense, every trench on Earth is a rehearsal for that search, a window into what life might look like elsewhere. The creatures that inhabit this lightless world have evolved senses and strategies that seem alien to us. Some fish have pressure-sensitive organs that can detect prey buried in sediment. Certain worms extend long filaments through the mud to absorb dissolved nutrients directly from the water. Amphipods communicate through touch and vibration, brushing antennae like signals in the dark. There's an intimacy to these interactions, a closeness born from necessity. When vision disappears, life becomes tactile, immediate, grounded in contact. Predation here is a quiet affair. There are no chases, no bursts of speed. A predator may wait motionless for hours, sensing the faint chemical trail of its prey, then lunge with a single slow strike. The prey, in turn, may respond with near-freezing stillness, relying on invisibility rather than flight. It's a world of patience, where the balance between hunter and hunted unfolds in centimeters rather than meters, in hours rather than seconds. The absence of light doesn't remove tension, it simply stretches it into a slower form. Every now and then, though, something extraordinary happens. A large disturbance, a quake, a landslide, or the collapse of a trench wall sends clouds of sediment billowing through the abyss. The water fills with fine particles, obscuring everything. For a while, visibility drops to zero. To us, it would look like chaos, but to the organisms here, it's opportunity. The shifting sediment brings with it nutrients trapped for centuries, releasing them into circulation. Microbes bloom, scavengers move in, and for a brief moment the darkness teems with activity. Then, slowly, the particles settle again, and stillness returns. Life in the world without sunlight is built on these cycles of disturbance and recovery. For humans, exploring this environment is one of the greatest technical challenges imaginable. Cameras must function in freezing temperatures and crushing pressure. Lights must be dim enough not to disturb, yet bright enough to capture detail. Robots must operate autonomously, following slow, deliberate paths. Each expedition to the Kuril Trench brings back data measured not in hours but in minutes of visibility. Yet every frame, every sample, adds another piece to the puzzle of how life endures without sunlight. What's remarkable is how unified the patterns are across the planet. The organisms in the Kuril Trench share similarities with those found in the Mariana and Tonga trenches. It's as if the deep ocean, separated by vast distances, still speaks a single evolutionary language. The pressures are different, the chemical compositions vary, but the adaptations converge. Transparency, softness, slowness. These are the universal traits of survival in darkness. Even here, far removed from the surface, the fingerprints of our species are present. Tiny microplastics have been found in the stomachs of amphipods collected from the trench. Synthetic fibres, likely from clothing, have settled into the sediment. Chemical traces of industrial activity have reached even these depths. It's a sobering reminder that the world without sunlight is not untouched. It is part of the same planet, connected through invisible threads of current and gravity. Yet even those traces become part of the ecosystem. Bacteria colonize the plastic, forming biofilms. The synthetic becomes organic. Life, as always, adapts. In the absence of light, the distinction between life and environment blurs. Many organisms are nearly indistinguishable from the sediment they live in. Some worms and crustaceans use mud as camouflage, coating themselves in it. Others have skin that reflects almost no light, blending perfectly into the darkness. Even movement becomes an act of invisibility. To survive here is to vanish. The absence of sunlight has not created a dead world. It has created a hidden one, a place where evolution's creativity is guided by pressure and chemistry, instead of colour and speed. The deep doesn't compete with the surface for beauty. It expresses it differently. In the world without sunlight, beauty lies in precision. The perfect balance between fragility and function, between existence and erasure. As we move along the trench floor, the quiet becomes deeper, the patterns of life more subtle. The pressure no longer feels like a force, but like the natural condition of being. The darkness is not an obstacle, but a background against which the smallest movement matters. Every detail becomes clearer. The faint swirl of sediment from a passing amphipod, the delicate imprint of a worm's track, the slow fall of a particle that may have begun its journey months ago near the surface. The world without sunlight isn't a void. It's a conversation that never needed light to begin with. And as we drift further, we start to encounter the strange inhabitants of the true deep. The creatures that have evolved forms and mechanisms unlike anything on land or even in shallower seas. The snailfish, the amphipods, the microbial mats are just the beginning. Below them lies another layer of mystery, where life takes on shapes so improbable that even naming them feels premature. They are the proof that existence continues to invent itself, even here, in the coldest and darkest places. That's where we go next, into the realm of those creatures that endure where physics itself seems unwilling to cooperate. a place where biology bends its own rules to keep moving forward, where life in its simplest forms becomes life at its most astonishing. When life sinks below the threshold where light no longer matters, the rules begin to change. The further we descend, the more pressure rewrites biology, and the creatures that exist here become living proof that nature has almost no limits. The Kuril Trench is one of those rare places where life doesn't just endure the impossible, it has made the impossible its natural state. Every organism here is an experiment that worked. Every movement, every chemical reaction, every fragile body plan represents a solution to a problem we can barely imagine. This is where the world becomes strange enough to seem alien, and yet everything about it is still deeply, unmistakably Earth. When scientists first managed to film the depths of the Kuril Trench, they weren't expecting to find much. They lowered cameras, baited traps, and waited, assuming that only a few hardy scavengers would appear. What came into view was a community of animals that seemed delicate, otherworldly, and yet completely at ease in a world of 1,000 atmospheres of pressure. There were translucent fish, pale amphipods, sea cucumbers gliding like balloons, and long, thread-like worms waving gently in the currents. Nothing rushed, nothing panicked. In the silence and cold, everything moved with measured grace, as though time itself had slowed to match the water. One of the most studied residents of this trench is the Hadal snailfish, the deepest living vertebrate known to science. It was filmed at depths of more than 8,000 meters, swimming in slow arcs above the sediment. To an untrained eye, it looks fragile, like a creature that could dissolve if touched. Its skin is gelatinous and nearly transparent, its fins soft and thin, but inside its biology is a masterpiece of adaptation. Without a gas-filled swim bladder, it doesn't need to fight buoyancy. Its bones contain very little mineral, making them flexible instead of brittle, and its cells are filled with a special molecule called trimethylamine N oxide, or TMO, which stabilizes proteins under extreme pressure. It's the same compound that gives many deep-sea fish their distinctive smell when brought to the surface, though down here it's simply a survival tool. The deeper the fish, the more TMAO it carries. At these depths, that chemistry becomes a shield against collapse. Even its behavior reflects a kind of optimization. The snailfish doesn't hunt in the way surface predators do. It drifts just above the sediment, using sensors along its body to detect movement. When it finds prey, usually amphipods or small worms, it opens its mouth slowly, creating a vacuum that draws the food in. No chase, no struggle, just precision. Each meal might be tiny, but in a place where energy is scarce, it's enough. Its entire design is centered on conserving energy while maximizing stability. The snailfish isn't fighting the deep, it's part of it. The amphipods, by contrast, are restless. These tiny crustaceans dominate the trench floor, thriving in places where few others can survive. They are the recyclers of the abyss, feeding on the constant fall of organic debris. Their bodies are transparent, their organs faintly visible inside. Some species reach astonishing sizes compared to their shallow water relatives, up to 10 centimeters long, an example of what scientists call deep-sea gigantism. The reasons for this are still debated. Some think it's due to colder temperatures and higher oxygen availability. Others suspect it's a side effect of slow metabolism combined with long lifespans. Whatever the cause, it makes the amphipods here look like ghostly giants drifting across a pale desert. They live fast compared to most deep-sea creatures, breeding in cycles that match the sporadic arrival of food. When a large meal appears, a whale carcass, a patch of decaying algae, they swarm in the thousands, stripping it to the bone. When food is scarce, they burrow into sediment, waiting for weeks without eating. Their digestive systems can slow almost to a stop, conserving every calorie. If disturbed, they dart upward, their bodies bending and releasing in quick, efficient bursts. In their movements, you can see both fragility and endurance, a paradox that defines almost everything alive in the deep, Among the amphipods live worms of countless kinds, polychaetes with feathery appendages, nematodes thinner than a hair, and ribbon worms that glide through the mud like living threads. Many of these species have never been named. Their diversity is staggering. In a handful of sediment, scientists can find dozens of species, each specialized to feed on slightly different materials. Some filter particles suspended in the water, others graze on microbial films, still others burrow deep into the mud, drawing in oxygen-poor water and extracting trace nutrients from it. To the naked eye, they might seem insignificant, but collectively, they keep the chemistry of the trench in balance, breaking down organic matter, cycling nitrogen, and making it possible for higher forms of life to exist. Further up the food chain are the predators, if that word even applies to a place where speed and aggression are useless. There are amphipods that feed on smaller amphipods, translucent fish that swallow prey half their size, and even gelatinous predators that drift silently, consuming anything that brushes against their bodies. Some of these hunters rely on bioluminescence to attract victims, while others have evolved long, sensitive appendages that act like radar, detecting movement through the dense water. The deeper one goes, the more these appendages dominate. Tentacles, whiskers, and filaments replacing eyes and teeth as the primary tools of survival. In the Kuril Trench, as in other Hadal zones, evolution seems to favour simplicity over ornamentation. The bodies here lack decoration. The colours are muted or invisible, and the forms are often minimal. Yet within that minimalism lies a kind of elegance. The amphipod's exoskeletons are almost glass-like, refracting what little light the submersible emits. The snailfish's soft outline seems to merge with the water itself. Even the worms that twist through the mud leave delicate trails that look like calligraphy written in silt. It's as though the absence of light has stripped life of everything unnecessary, revealing only what works. But not all life here is quiet. Some organisms have turned the constant pressure to their advantage. Certain species of deep-sea holothurians, sea cucumbers, have evolved the ability to inflate and float using water rather than gas. They pump water into internal cavities, adjusting their buoyancy so precisely that they can hover motionless above the seafloor for hours. When threatened, they release sticky filaments to entangle predators or simply deflate and sink back into the sediment. Others have translucent sails or fins that catch the faint currents, allowing them to drift vast distances without effort. Watching them on camera is like watching a slow ballet of soft shapes, rising and falling with invisible rhythm. Some of the most bizarre creatures in the deep belong to the gelatinous families, ctenophores, jellyfish, and siphonophores that can reach lengths of several meters. Unlike their shallow water relatives, these deep-dwelling versions often lack bright colors or visible light. Instead, they rely on transparency to disappear completely. A few still produce faint glows when disturbed, flashes of blue-green light that ripple through their bodies like electrical pulses. These displays may serve as warnings or mating signals, but they also create a haunting beauty in a place where beauty seems impossible. Microbes, though invisible to the camera, are the true majority here. Their populations number in the trillions within a single cubic meter of sediment. Many feed on chemical reactions involving sulfur, methane, or even hydrogen. Some live inside the bodies of larger animals, forming symbiotic relationships that allow both to survive. Others live in the rocks themselves, in tiny pores and fractures where they are protected from predators and currents. Their metabolism is so slow that entire generations may pass in the time it takes a tree to grow. Yet their collective activity maintains the chemical balance of the trench, transforming minerals and gases in ways that ripple upward through the food web. It's strange to think that in a world so devoid of light, cooperation might be more common than competition. Many of these creatures live in partnerships that blur the line between individual and environment. Tube worms at seeps host bacteria within their tissues, providing them with space and nutrients in exchange for food. Some amphipods carry symbiotic microbes on their shells that help them digest tough materials. Even the snailfish likely relies on bacteria in its gut to process the strange compounds it consumes. Survival here isn't about domination, it's about equilibrium. The more scientists study these creatures, the more they realise how finely tuned they are to their environment. When brought to the surface, most of them die within minutes, their bodies destroyed by the sudden drop in pressure. This makes studying them a delicate task. Special pressurised containers have been developed to keep samples alive during the journey upward, allowing researchers to observe their behaviour without disturbing their internal balance. What they've learned has challenged almost every assumption about biology. Proteins that should denature at extreme pressure remain stable. Membranes that should rupture remain flexible. Even DNA, which can be damaged by radiation and heat, appears to repair itself more efficiently here, perhaps because of the steady conditions. These discoveries have implications that reach far beyond marine science. The enzymes of deep-sea organisms are now being studied for industrial and medical applications, from pharmaceuticals that remain stable under stress to enzymes used in food processing and biotechnology. The same chemical principles that keep a snailfish alive under pressure might one day help design materials or medicines that endure extreme environments. In that sense, the deep is not just a mystery to explore, but a library of solutions waiting to be read. The behaviour of these creatures also holds lessons about resilience. Life here is slow, cautious, deliberate. Nothing is wasted. Each species has found a way to live within limits so strict they would seem unlivable anywhere else. Yet instead of shrinking, they've diversified. The trench is not a desert, but a mosaic of microhabitats, ridges, slopes, plains and seeps, each supporting its own community. Some species prefer the softer sediments of the floor, others cling to rocky outcrops along the walls. Some feed near seeps where chemical energy flows, others drift through the mid-water zone, feeding on whatever falls. The more we look, the more variation we find. Even in the deepest shadows, evolution never stops experimenting. It's tempting to describe these creatures as alien, but that word only shows how narrow our frame of reference is. They are as earthly as any sparrow or oak tree. The difference is that they've adapted to a set of physical laws most of us will never experience directly. To them, 1,000 atmospheres of pressure isn't a barrier, it's the normal state of existence. The lesson isn't that they are strange, but that our idea of normal is small. The crushing deep reveals not how different life can be, but how broad the concept of life truly is. Occasionally researchers catch glimpses of movement that doesn't match any known species. A long ribbon-like shadow drifting across the camera. A burst of bubbles followed by silence. A faint, slow undulation in the background that disappears before focus can adjust. These moments remind us that even after decades of exploration, most of the trench remains unseen. The total area explored by human eyes or cameras covers less ground than a city block. For every snailfish recorded, there are likely dozens of species that have never been observed. The deep keeps its secrets, not out of malice or mystery, but simply because time moves differently here. The Kuril Trench is one of several Hadal trenches circling the Pacific, and comparisons between them reveal fascinating differences. The amphipods here tend to be larger than those in the Mariana Trench. The snailfish here swims slightly shallower, perhaps because of temperature or nutrient differences. Each trench becomes a kind of laboratory where evolution runs variations on the same theme. The pressures are constant, but the inputs, sediment composition, chemical seepage and tectonic activity change. Over millions of years, those small differences sculpt distinct ecosystems. To study them is to watch nature repeat itself with infinite nuance. For the animals of the deep, even death is part of the cycle. When a creature dies, its body quickly becomes a resource. Bacteria begin the decomposition. Amphipods arrive, worms follow. The organic matter is broken down, recycled and absorbed back into the sediment. Nothing is lost. In the world of crushing pressure, decay is just another form of persistence. The boundaries between living and dead blur. A single bacterium might spend part of its existence in one body, then drift into the sediment to feed another. It's an ecosystem that wastes nothing, that turns the end of one existence into the beginning of another without pause. And while all this unfolds in the dark, the surface world above remains unaware. Waves roll over the trench, ships pass, storms sweep across the Pacific, and the creatures below continue their slow, silent routines, unchanged. To them, the events of the surface, seasons, tides, weather, are irrelevant. Their environment is constant, predictable, and eternal within its own scale. They don't need sunlight to know time. They measure existence by movement, by the slow drift of particles, by the frequency of disturbance. To them, that's the rhythm of life. The more we observe these creatures, the clearer it becomes that they're not just surviving, they're thriving. Evolution hasn't merely tolerated the crushing deep, it has mastered it. Each organism is a different solution to the same challenge, and each solution reveals something about what life can do when pushed to its limits. The Hadal zones like the Kuril Trench aren't the edge of habitability, they're the continuation of it. They show that even under the weight of 10 kilometers of water, life doesn't give up. It adapts, it diversifies, and it finds ways to turn pressure itself into an ally. As the submersible's lights fade into the distance and the last glimpse of these creatures disappears back into the dark, the sense of strangeness lingers, but it's not fear or discomfort, it's recognition. The world of the crushing deep is the world that made us, the same ocean that once gave rise to everything living on land. These creatures are not strangers. They are our distant relatives, shaped by the same physics, the same chemistry, the same persistence of matter that defines all life. And deeper still, beneath them, the landscape continues to change. The walls of the trench curve inward, the sediment thickens, and the water grows even denser. The creatures fade one by one, replaced by simpler forms, microbes, archaea, and chemical reactions that blur the line between biology and geology. This is the next threshold, where survival becomes an art of molecules, and the story of life begins to merge with the story of the planet itself. That's where we drift next, into the realm of bone and mineral, of adaptation written in the very structure of cells, the place where the architecture of survival reveals itself not in motion but in design. Down here, everything that exists must answer a simple question. How do you keep your form when the world is trying to crush you? The trench tests that question in every way possible. At these depths, even the smallest miscalculation in design means collapse. Bones shatter, shells implode, membranes rupture. Survival becomes a kind of architecture, a balance between strength and surrender. The creatures that endure in the Kuril Trench have each solved that balance differently, building bodies that follow laws no engineer would invent yet that function flawlessly in the deep. Studying them is like watching evolution practice material science at pressures no laboratory can reproduce. What makes this survival so fascinating is that it's not achieved through brute force. There are no thick shells or heavy skeletons here. Those would only add stress. Instead, the strategy is to remove, to lighten, to simplify. The most successful structures are the ones that yield. The Hadal snailfish, for instance, has bones so soft they bend rather than break. Its skull is not a single solid piece, but a mosaic of thin plates connected by cartilage, allowing it to deform slightly under pressure and return to shape afterward. Its internal organs are surrounded by water of nearly identical density to its tissues, eliminating the difference that would otherwise crush it. Every part of its design accepts pressure instead of resisting it. Other animals achieve the same harmony through entirely different means. Deep-sea amphipods, for example, build their exoskeletons from chitin, the same material used by shrimp and insects at the surface, but with less mineralization. At the same time, they reinforce those shells with aluminum, an element they extract directly from seawater, using acidic secretions in their guts. It's an elegant solution. Aluminum forms a gel-like coating that makes their exoskeletons more flexible, while preventing dissolution in the high-pressure, low-pH environment. No human material scientist had imagined that process until these small crustaceans revealed it. Their shells are quite literally works of chemistry in motion. Pressure doesn't just affect hard parts, it also transforms the chemistry of soft tissues. Proteins, which form the machinery of cells, are sensitive to deformation. Under extreme pressure, they can unfold or lose function. To prevent this, deep-sea organisms modify their internal fluids, filling them with compounds that stabilize protein structure. Trimethylamine N-oxide, TMAO, is one of these molecules, but it's not alone. Some bacteria produce unique amino acids that act as microscopic scaffolds, keeping proteins folded and active. Others use sugars or alcohol-like molecules to maintain flexibility. The result is a living solution, a fluid chemistry perfectly tuned to its surroundings, capable of sustaining metabolism even at crushing depths. For those that rely on shells, the challenge is different. In the upper ocean, shells are made mostly of calcium carbonate, which forms readily in alkaline low-pressure water. But in the deep sea, where pressure increases and temperature falls, calcium carbonate becomes unstable and begins to dissolve. To build shells here, organisms must find alternatives. Some use different minerals entirely. Silica, for instance, is seen in deep-sea sponges whose skeletons are made of glass-like fibers. Others coat their shells in organic layers that resist dissolution. The small foraminifera living along the trench slopes construct intricate tests, from fine grains of sediment glued together with secreted proteins. Seen under a microscope, these shells look like miniature sculptures, spheres, spirals, and lattices assembled grain by single-celled architects. Each one is a perfect compromise between strength, lightness, and resilience. What's remarkable about these adaptations is how widespread they are. Every layer of the trench, from the upper slopes to the deepest basin, hosts species that have independently solved the same physical problem. The variety of strategies shows how evolution explores every possible route to stability. In some species, shells are reduced to thin films. In others, bones are replaced with flexible rods. Some creatures avoid hard structures entirely, adopting soft, jelly-like bodies that equalize pressure through uniform density. This diversity of approaches forms a kind of living catalogue of mechanical solutions, an encyclopedia of how to exist under weight. The art of survival here isn't only physical, it's chemical and behavioural too. Some organisms, like certain deep-sea worms, secrete mucus cocoons that create microenvironments around their bodies. Inside those bubbles, pressure is still immense, but chemical conditions, such as pH and oxygen levels, can be slightly adjusted. It's enough to stabilize enzymes and extend lifespan. Others form partnerships that distribute the burden of survival. Microbes living inside larger hosts share metabolites and help neutralize toxins. In return, the hosts provide a stable habitat and protection from predators. It's not unlike architecture built cooperatively, each participant reinforcing the other's weaknesses. Bones themselves tell a story of adaptation. When brought to the surface, the skeletons of hadalfish appear almost fragile, bending under their own weight. Yet in their natural environment, those same bones function flawlessly. The difference lies not only in structure but in purpose. These bones aren't designed to support the body against gravity. They're designed to maintain form in a world where gravity is balanced by buoyancy. Their function is less about bearing weight and more about organizing tissue. The result is a skeleton that's light, flexible, and distributed, more like scaffolding than framework. It's a reminder that structure doesn't always mean rigidity. Sometimes it means balance. Among the most striking examples of this principle are the gelatinous animals that drift through the trench water. Their bodies are almost entirely water, with only a thin framework of connective tissue giving them shape. Yet they maintain perfect form under pressures that would flatten steel. Their secret is equilibrium. The fluids inside their cells match the surrounding seawater so closely that there's no internal stress. The same pressure that pushes inward from the outside also exists within, creating a perfect standoff. To the human mind, this seems counterintuitive. How can something so soft endure such force? But that's the beauty of it. The deep doesn't reward resistance, it rewards harmony. Even mineralized structures follow that rule. Deep-sea corals found at shallower slopes near the trench edge grow skeletons of aragonite, a form of calcium carbonate that resists dissolution under pressure. But they grow slowly, almost imperceptibly, adding microscopic layers each year. Some specimens have been found to be thousands of years old, their skeletons recording changes in ocean chemistry across centuries. Each layer tells a story of adaptation, a timeline written in mineral. To these corals, survival isn't about speed or size, it's about patience, about enduring long enough to outlast the conditions that threaten them. In the sediment, another kind of architecture forms, biogenic structures built by burrowing creatures. Small shrimp and worms dig tunnels that allow water to circulate, oxygenating the layers below and redistributing nutrients. Over time, these tunnels collapse and reform, creating a dynamic texture beneath the surface. It's a kind of engineering that happens without intention, but with perfect effect. The sediment remains alive because of it. Without these small architects, the trench floor would stagnate, suffocating under its own weight. Instead, it breathes slowly and steadily through the collective labour of its smallest inhabitants. Survival here is as much about chemistry as it is about design. The metabolic pathways of deep-sea organisms have evolved to function under low oxygen and high carbon dioxide levels. Their cells use enzymes that operate efficiently even when energy is scarce. Some can switch between aerobic and anaerobic metabolism, adjusting to the availability of oxygen like a dimmer switch. Others rely on symbiotic bacteria to break down complex compounds they can't process themselves. It's not a single adaptation, but a system of small adjustments that together make existence possible. To the human eye, these adaptations may seem extreme, but they're not exceptions. They're the natural outcome of persistence. Life has been testing this environment for billions of years. Every shell, every bone, every membrane represents countless generations of trial and error. Evolution doesn't design with foresight, it improvises, tinkers, and refines. The creatures of the Kuril Trench are the result of that endless refinement, the successful survivors of conditions most living things would find intolerable. Pressure also shapes reproduction. Many species here lay fewer eggs than their surface relatives, but each egg is larger, filled with more nutrients to sustain development in slow, cold water. Some eggs are encased in tough membranes that resist pressure changes. Others develop directly into miniature adults, bypassing the vulnerable larval stages. Brooding is common. Female amphipods carry their young in pouches until they're ready to survive on their own. The same pattern appears in certain deep-sea fish. Reproductive success isn't measured in numbers but in longevity. Each offspring represents an enormous investment of time and energy, and survival depends on precision rather than abundance. The trench environment shapes not only the bodies of its inhabitants but their behaviours. Movement is slow, deliberate, and efficient. Some species remain in place for years, feeding from the same patch of sediment. Others migrate vertically by a few meters, following chemical gradients instead of light. Communication, when it occurs, is subtle. Chemical signals released into the water, vibrations through the sediment, or, rarely, flashes of light. These cues help coordinate mating, feeding, and defense, though to an observer, they're invisible. It's communication suited to a world where distance and delay define everything. Even in death, the deep's inhabitants contribute to the architecture of survival. The remains of shells and bones accumulate in the sediment, forming a record of generations past. Over time, these materials compact and become part of the geological layer, preserving traces of proteins and minerals. Some of these deposits can last for millions of years, eventually being subducted into the Earth's mantle along with the descending plate. In that sense, the shells and bones of trench dwellers literally return to the planet's interior, recycling not just matter but history. The cycle is complete. What begins as life ends as stone, and what becomes stone may someday feed life again. There's a quiet lesson in that cycle. On the surface, survival often seems tied to dominance, to growth, competition, and strength. In the deep, survival means balance, adaptation, and restraint. Every organism here is an example of efficiency perfected over time. Their bones and shells aren't armour, they're agreements with the environment, contracts that allow existence to continue without conflict. The art of survival here isn't about defiance, it's about acceptance. This philosophy of endurance extends to the microbial level. The bacteria that live within rocks along the trench walls survive with almost no nutrients, metabolizing trace amounts of hydrogen or sulfur compounds. Their division rates are astonishingly slow, once every few months or even years, but that slowness allows them to persist indefinitely. They repair themselves when damaged, share genetic material with neighbours, and maintain balance across generations. They are the planet's minimalists, proving that life doesn't need abundance to endure, it needs only persistence and structure. Scientists studying these communities often describe them as living fossils, not because they are ancient in form, but because they represent processes that have existed since the dawn of life. The earliest organisms on Earth likely lived in similar conditions, dark, pressurized, chemically rich. The adaptations we see in the Kuril Trench aren't new inventions, they're continuations of strategies billions of years old. The trench isn't just a window into an extreme ecosystem, it's a window into our origins. Every shell, every enzyme, every cell down here carries echoes of the first forms of life that appeared when the planet was still cooling. As the submersible drifts along the trench wall, the lights reveal occasional glimmers, shell fragments, mineral veins, the reflective sheen of an amphipod's carapace. Each shimmer is a reminder that even in the darkest depths structure endures. The bones and shells scattered across the seafloor are not signs of loss, but of continuity. They mark the boundaries between past and present, between life that was and life that is. They show how survival, over time, becomes inheritance. And deeper still, beyond even these layers of fragile design, lies a region where the architecture of life begins to merge with the architecture of the planet itself. A zone where rock and biology intertwine, where the language of survival becomes indistinguishable from the language of chemistry. That is where the story continues, where existence in the abyss reveals its next form, not just life surviving, but life communicating in silence, through vibration, energy, and movement. In the deep ocean, sound replaces light as the dominant sense. Vision fades, colour disappears, and movement slows until the only reliable way to perceive the world is through vibration. The Kuril Trench, silent to human ears, is alive with pressure waves and resonances that form a language older than speech. Every tremor, every current, every shift of sediment produces sound. It's faint, low, and constant, a background pulse that never ceases. For the creatures that live here, those vibrations are everything. The texture of space, the memory of distance, the signal that something else is near. Sound travels differently under pressure. In air it fades quickly, losing energy as it passes through molecules far apart from each other. In the deep ocean, where molecules are dense and compressed, sound moves faster and farther. A single pulse can travel hundreds of kilometres, bouncing off the trench walls like an echo inside a cathedral. The water conducts it perfectly, wrapping it around curves, guiding it along slopes, and blending it into a continuous hum. To us, that hum is almost silent. To the animals that depend on it, it's the fabric of their world. Hydrophones placed along the Kuril Trench have recorded a soundscape that's more complex than the quiet surface suggests. There's the constant murmur of microseisms, tiny vibrations caused by distant waves crashing against continents. There are the crackles of bubbles rising and collapsing, the faint grind of sediment shifting down slopes, and the low-frequency groan of tectonic motion. Mixed in are biological sounds, the clicks and snaps of crustaceans, the soft pulses of deep-sea fish, and occasional bursts of noise that remain unidentified. Some of these sounds follow patterns, repeating in rhythms that suggest communication. Others are random, accidental, the byproducts of movement and feeding. Together they create an invisible symphony that never stops playing. Communication here doesn't follow our concept of language. It's not symbolic or structured, it's contextual, each sound a signal embedded in its environment. For example, a sudden vibration in the sediment might warn nearby animals that a predator is approaching. A rhythmic pulse could signal territory or mating readiness. The meaning is in the pattern, not in the sound itself. Even chemical signals and electrical fields become part of this exchange. In a place where energy is precious, information is never wasted. Every sound has purpose, even if we don't understand it. Many deep-sea species have evolved organs specifically for detecting these subtle vibrations. Fish in the Hadal zone often possess extended lateral line systems, rows of fluid-filled canals along their bodies lined with sensory hair cells. When water moves, those hairs bend, triggering nerve impulses that translate motion into perception. It's a kind of touch at a distance. Through it, they can sense the movement of prey, the flow of currents, or the presence of other fish even in total darkness. Some species can detect vibrations as faint as a few nanometers, smaller than the width of a bacterium. Their entire awareness is built from motion. Other species go further, producing sounds intentionally. Deep-sea grenadiers, for instance, are known to emit low-frequency drumming noises by vibrating their swim bladders or specialized muscles. These sounds are thought to serve as mating calls or social signals. Certain crustaceans create snapping or tapping noises by striking parts of their exoskeleton together. In the shallower ocean, these snaps can form dense choruses, audible for kilometers. In the trench, they occur more sporadically, isolated but distinct. Each snap, each pulse, is a statement, an announcement of presence in a world where sight and colour no longer exist. The trench itself amplifies and shapes these sounds. Its walls act like a natural resonator, focusing vibrations and guiding them along the curve of the seafloor. When earthquakes occur, the energy reverberates for hours, creating infrasonic waves that travel through the water column. Some animals appear to respond to these events, changing their behaviour days before a quake. It's possible they sense micro-vibrations that precede major movements, or chemical cues released by shifting rock. Whatever the mechanism, they're attuned to the Earth's voice in ways we can barely imagine. For humans, listening to the deep requires technology. Arrays of hydrophones record frequencies far below the range of human hearing, later sped up and translated into audible sounds. What we hear when we play them back is haunting. Low hums, groans, and rhythmic thuds like a slow heartbeat. Sometimes in those recordings, patterns emerge that don't fit geological or known biological sources. Slow, repeating tones, pulses that rise and fall. Scientists are cautious about labeling them, but they stand as reminders that communication in the abyss may operate on levels we don't yet recognize. Chemical signaling is another form of language below. Many deep-sea organisms release molecules that drift through the water, carrying information about species, sex, reproductive state, or territory. These molecules are detected by chemoreceptors, sensory cells far more sensitive than anything humans possess. A single molecule in 1 million litres of water can trigger a response. To us, that seems miraculous. To the deep, it's routine. Smell, in this sense, is as important as sound. It's a slow form of communication, spreading through currents, lingering for hours or days. When a snailfish releases a trace of pheromone, it's not calling to a nearby mate. It's sending a message across invisible distance, one that the current will deliver in time. Electrical fields also play a role. Some fish and invertebrates generate weak electric currents through their muscles or specialized organs. Others can detect those fields, using them to locate prey or navigate. In the deep, where magnetic fields fluctuate and light offers no guide, electricity becomes a map. Sharks, rays, and certain catfish species are famous for their electroreception in shallower water, but similar abilities have evolved independently in deep-sea species. These electric senses blur the line between perception and interaction. The moment one animal moves, it leaves an electrical footprint that another can follow. It's a dialogue of energy, silent and instantaneous. Even at the microbial level, communication persists. Bacteria use chemical signaling known as quorum sensing to coordinate behavior. When enough cells release specific molecules, the concentration reaches a threshold that triggers a group response. Perhaps the formation of a biofilm, the release of enzymes, or the activation of dormant genes. It's not conscious, but it's collective. In the Kuril Trench, microbial communities spread across rocks, and sediments respond to each other this way, synchronizing activity across large areas. To an outside observer, it looks like the seafloor itself is breathing in patterns. The smallest forms of life here act in concert, turning chemistry into chorus. What's fascinating is how these different modes of communication, sound, vibration, chemical, and electrical, overlap. They create a multi-layered network of signals that binds the ecosystem together. A disturbance in one part of the trench sends ripples that others can detect. The fall of a carcass, the rumble of a quake, even the slow drift of a current, each becomes part of the collective awareness. In a way, the trench is a single, continuous organism with its inhabitants acting as its sensory cells. The echoes in the dark aren't just noise, they're feedback, a way for the system to sense itself. Human attempts to map this acoustic world have only scratched the surface. Deep-sea hydroacoustic monitoring began as a military tool, designed to track submarines during the Cold War. When the data was later analysed by scientists, it revealed an ocean alive with sound. Whales calling across entire basins, ice cracking in the poles, volcanoes erupting beneath the waves, and mysterious low-frequency signals with no clear source. Some of those signals originated near the Kuril Trench, their patterns repeating seasonally, perhaps linked to migrations or geological activity. The more we listen, the more complex the ocean's voice becomes. Listening also teaches humility. The sounds we make, ship engines, sonar pulses, drilling operations, travel vast distances underwater. They enter this quiet realm uninvited, masking natural signals and disrupting communication. Studies have shown that certain deep-sea species become disoriented or alter their behaviour in response to human noise even at low intensities. In the trench, where every vibration matters, such interference is profound. The echoes in the dark are delicate, and we've already begun to reshape them without realising it. Yet even amid that disruption, the deep adapts. Species shift their frequencies, adjusting to avoid interference, much like birds change their calls in noisy cities. Some fish have been observed using higher or lower tones than usual when exposed to artificial sound. Life finds new bandwidths, new rhythms, new ways to speak. The language of the abyss is flexible, capable of evolving in real time. That adaptability may be its oldest strength. When you consider how dependent these creatures are on sound, it becomes clear that silence here doesn't mean absence, it's context. The pauses between vibrations, the moments of stillness, carry as much information as the sounds themselves. In those gaps, animals sense changes in pressure, temperature, and current. They feel the ocean's breath. Communication here isn't a series of messages, it's continuous awareness. To exist in the trench is to listen always, to be attuned to the faintest shift in the water's body. For researchers, that awareness is something to strive toward. To study the deep, one must learn to interpret indirect signals, to read vibrations and chemical traces instead of sights and sounds. Instruments become extensions of the senses, translating an environment built on resonance into data we can understand. Each measurement, each recording, is a small attempt to bridge the gap between two forms of perception. We're trying to listen to a world that never needed us to hear it. Sometimes, when data's played back, patterns emerge that feel almost intentional. Pulses recurring every few seconds, growing faster and then fading. Long, drawn-out tones that modulate in frequency. Clusters of clicks forming complex structures. Scientists classify them carefully, some as known animal sounds, others as unidentified biological. But there's a quiet wonder in imagining what they might represent. Mating calls, navigation signals, group coordination. The truth is that even now, most of what communicates in the abyss remains unknown. The ocean is speaking constantly. We've only begun to decipher the first syllables. There's an elegance to this form of life, a collective existence defined by sensitivity rather than dominance. The trench isn't a place of isolation, but of connection, built on signals too subtle for us to perceive unaided. The creatures here live in a perpetual exchange of motion, energy, and information. They don't need eyes or voices because they are already immersed in the medium of communication itself. Every ripple is a sentence, every tremor a response. The language of the deep doesn't travel through air, it travels through being. And perhaps that's the most profound truth hidden beneath the silence. In this darkness, communication isn't separate from survival. To hear is to exist. To sense is to persist. The trench's inhabitants aren't just reacting to their world, they're participating in its constant conversation. It's a form of life where awareness and existence are the same thing, woven together by sound and motion. As the instruments fall quiet and the submersible drifts further down, the sounds thin out again, replaced by a lower, slower rhythm. The earth itself moving, grinding, sighing beneath the weight of the sea. The echoes in the dark fade, merging into that steady pulse. Below this level, communication shifts once more. The world becomes less about sensing others and more about sensing the planet. Life continues, but its language changes, becoming chemical again, mechanical, almost geological. That's where the descent leads next, to the hungry machine at the bottom, where the last fragments of sunlight-born life are broken down and repurposed, where the echoes of existence become sustenance, and where the deep turns the fallen into fuel for what follows. At these depths, nothing truly dies. Everything that falls is taken, stripped, dissolved, and reassembled into new forms of life. The deep ocean doesn't waste, it consumes and transforms with perfect precision. The Kuril Trench, more than almost any other place on Earth, operates like a slow mechanical heart, recycling the remains of the surface world into the foundation of the abyss. The creatures that inhabit it are part of a single, vast metabolism, a hungry machine built from countless mouths and microbes, each performing its task in silence. When something from above dies, a jellyfish, a fish, or a whale, it begins a long descent through the water column. The fall can take days or weeks depending on size. Along the way, smaller creatures nibble at the body, peeling away soft tissue, scattering fragments, and releasing a storm of organic debris. By the time what's left reaches the depths of the Kuril Trench, it's already been reduced to a framework of bone and fat. Yet down here, even that is treasure. For the inhabitants of the abyss, each carcass is an island of abundance drifting into the desert of the seafloor. The moment a body touches bottom, the transformation begins. Amphipods arrive first, hundreds, then thousands, swarming with a coordinated intensity that looks almost choreographed. They tear into the tissue, consuming everything soft within hours. Then come the worms, polychaetes and nematodes, sliding through the sediment to feed on whatever remains. Their movements stir the water, releasing clouds of particles that attract bacteria. Within days, the surface of the carcass is covered in a fine film of microbial life. The process is both violent and elegant, a choreography of necessity. Bacteria and archaea are the true engines of this system. They release enzymes that break down complex organic molecules, fats, proteins, collagen, into simpler compounds. As they work, they produce gases and chemicals that attract new organisms. Sulfide-loving microbes colonize the bones, feeding on the fats trapped within. They release hydrogen sulfide, a compound toxic to most life but essential here. Other bacteria consume that sulfide, using it to drive chemosynthesis. The result is a self-sustaining community built entirely from decay. Each generation of microbes gives rise to the next, forming layers of activity that turn death into energy. In the case of a whale fall, the process can last decades. After the soft tissue is gone, the skeleton becomes the focus. Specialized worms, known as osedacs, burrow into the bones. They have no mouths or stomachs. Instead, they use root-like structures to dissolve bone material and absorb nutrients through symbiotic bacteria living inside them. These bacteria convert the fats and collagen into usable energy, feeding both themselves and their hosts. The worms reproduce quickly, sending larvae into the water to search for new carcasses. Many never find one. The deep is vast and whale falls are rare, but the few that succeed continue the cycle, spreading this strange partnership wherever death descends. Smaller carcasses follow a similar pattern on a different scale. When a squid or large fish falls, amphipods dominate the early stages. Their feeding breaks the body apart, allowing bacteria to penetrate deeper. Some amphipods carry bacterial colonies on their shells, effectively transporting decomposers from one meal to another. As the remains shrink, the ecosystem shifts. Microbial mats form around the bones, then disperse once the nutrients are exhausted. The process leaves behind only a faint stain on the sediment, a chemical signature that persists for months before disappearing. This recycling system extends far beyond visible remains. Even the constant drizzle of marine snow, the steady fall of tiny organic particles, feeds the deep. Each particle is a fragment of life from above, bits of plankton, fecal pellets, fragments of shells, or aggregates of mucus and dust. As they sink, they are colonized by bacteria, which consume part of their carbon content and release the rest as dissolved compounds. By the time they reach the trench, they've become nutrient-rich microhabitats, supporting miniature communities of microbes and tiny crustaceans. Collectively, this continuous rain sustains much of the deep-sea ecosystem. The machine is always fed, even when no great carcass falls. What's remarkable is how efficient this system is. In shallower waters, much of the organic matter decomposes before reaching the bottom. In the trench, where temperatures are near freezing and oxygen levels low, decomposition slows. Organic material can persist for years, releasing nutrients gradually. This slow release feeds a constant background of microbial activity. The abyss doesn't rush. Its metabolism is slow, steady, and perfectly tuned to scarcity. Every organism is part of a chain that stretches from the surface to the sediment, from living tissue to dissolved carbon. Some of the most important participants in this system are invisible. Deep-sea bacteria capable of digesting complex compounds, keratin, collagen, even plastics, play a central role in recycling. They transform materials that would otherwise accumulate, breaking them down into simpler molecules that other organisms can use. These microbes are incredibly diverse. Genetic analyses reveal thousands of species, many unique to specific depths or types of sediment. Each one occupies a narrow ecological niche, specializing in a particular substrate or chemical condition. Together, They form a biochemical network that rivals the complexity of any rainforest. Chemical gradients drive this machinery. As organic matter decays, it consumes oxygen, creating zones of anoxia where other reactions take over. Nitrate and sulfate reduction become dominant, producing nitrogen gas, hydrogen sulfide, and methane. These gases in turn feed chemosynthetic microbes. It's a chain reaction that converts the energy of the surface world into chemical potential. The entire trench operates as a massive biogeochemical reactor, processing the remains of life into the raw materials for more life. The role of pressure in this process is subtle, but profound. Under high pressure, chemical reactions proceed differently. Gases dissolve more easily, enzymes behave uniquely, and diffusion slows. Microbial metabolism adapts accordingly. Some deep-sea bacteria rely on pressure-sensitive enzymes that function only under extreme conditions. When brought to the surface, these enzymes denature, and the cells die. To the microbes of the Kuril trench, the crushing weight above is not a burden, it's a required ingredient for life. The hungry machine cannot function without it. Even inorganic materials are drawn into this cycle. Metals like iron, manganese, and copper are released during decomposition and incorporated into bacterial enzymes or precipitated into mineral nodules. These nodules, found scattered across the trench floor, grow at microscopic rates, millimeters per million years, but they record the chemical history of the ocean. Each layer captures the balance of elements in the water at the time it formed, creating a timeline of the deep's metabolism. Some nodules contain traces of organic matter embedded within them, fossilized remains of microbes that once fed the machine. Feeding in the abyss isn't limited to scavenging and decomposition. Some organisms have evolved to exploit the byproducts of decay directly. Methanotrophic bacteria, for example, consume methane produced by decomposition and use it to power chemosynthesis. They form mats on the sea floor, which attract small grazers like snails and amphipods. The grazers feed on the bacteria and in turn are eaten by larger predators. It's a secondary food chain built entirely from the chemistry of rot. In the Kuril trench, this process blurs the line between decay and growth. The machine consumes itself endlessly, each stage feeding the next. There's a sense of balance in the system, a kind of quiet order. When a large influx of organic matter arrives, bacterial populations surge, consuming oxygen and releasing sulfides. When the supply dwindles, the community contracts, leaving behind dormant cells that can survive for years without food. The trench adjusts to these fluctuations automatically. It's self-regulating, self-repairing. Unlike ecosystems at the surface, which can collapse from imbalance, the abyss endures because it operates at a slower pace. Its hunger is constant but measured. The creatures higher in the food web play their part too. Sea cucumbers, worms, and small crustaceans process sediment continuously, passing it through their bodies and extracting whatever nutrition remains. Their waste in turn fuels bacterial growth. This endless recycling ensures that almost nothing goes unused. The sediments of the trench are alive in a way that defies the word. Every grain is coated in bacteria. Every pore holds a micro-ecosystem. To disturb it is to disrupt a system so intricate it has no beginning or end. Human observers often describe this process in mechanical terms, a biological engine, a conveyor belt of decay, but it's more accurate to think of it as a conversation between matter and energy. The hungry machine isn't just eating, it's translating. What falls from the surface is transformed into a language the deep can understand. Molecules rearrange, bonds break and reform, and the result is life reconstituted. The system isn't consuming so much as converting. It's the planet's original recycling program, perfected over billions of years. Even the smallest details of this process reveal complexity. The rate of decomposition depends on temperature, oxygen levels, and pressure. Seasonal variations in surface productivity can affect how much organic matter reaches the trench months later. A bloom of plankton in spring might feed bacteria in the abyss by winter. Everything is connected by invisible delay. The hungry machine operates not in real time, but in echoes of the surface world. It's a time-shifted mirror of life above, responding to events long after they've passed. This delayed connection has another effect: stability. Because the deep receives a constant but filtered input from above, it's insulated from short-term fluctuations. While the surface ocean reacts rapidly to storms, climate shifts, and human activity, the trench processes those changes slowly. It's a buffer, a stabilizing force in the global carbon cycle. By trapping and transforming organic matter, it prevents carbon from returning immediately to the atmosphere. The deep ocean and trenches like Kuril act as the planet's long-term carbon sink. In that sense, the hungry machine feeds not just itself but the entire biosphere. The deeper scientists look, the clearer it becomes that the trench's metabolism resembles the inner workings of a living organism. The inflow of organic matter, the transformation through microbial digestion, the release of gases and minerals, all mirror biological processes on a planetary scale. The Kuril Trench is, in effect, part of the Earth's circulatory system. What dies at the surface becomes nourishment for the deep, and what the deep processes becomes foundation for the future. Even continents owe their stability in part to this exchange. The sediments that sink into trenches carry with them the remains of ancient oceans, storing their carbon and nutrients for millions of years. Within this slow, relentless consumption lies a kind of peace. There's no waste, no tragedy and death here, only continuation. The amphipod feeding on decaying flesh, the bacterium oxidizing methane, the worm tunneling through sediment. They're all participants in the same process, each stage leading seamlessly into the next. The hungry machine is not cruel, it's efficient. It doesn't mourn or celebrate, it simply endures. And as this process unfolds over eons, it leaves behind structures, fossilized traces of microbial mats, mineralized bones, the chemical shadows of once living things. These records tell a story not just of feeding, but of balance, of how the deep ocean maintains the planet's long-term rhythm. It's a rhythm too slow for human senses, but it's the pulse that underlies everything. Even the sound of this system can be heard if you know how to listen. Hydrophones have detected faint clicks and crackles from microbial activity, the release of gas bubbles, the shifting of sediment as decomposers work. It's almost imperceptible, but it's there. The sound of the hungry machine at work, steady, constant, eternal. The deeper you understand it, the more it resembles not just a biological process, but a philosophy. Nothing wasted, nothing idle, everything reused. The deep is not a graveyard, it's a workshop, an engine, a recycling plant built entirely from patience and necessity. It turns what the world discards into the foundation for new life, and deeper still, below this realm of feeding and transformation, lies the boundary where biology begins to give way to geology. The chemical gradients sharpen, the sediments compact, and the heat from the earth below begins to rise. The hungry machine extends its reach downward, merging with the slow, unseen factories of the crust itself. There, life persists in its simplest, most enduring form, feeding not on what falls from above, but on the chemistry of the planet itself. That's where we descend next, into the hidden furnaces beneath the seafloor, where heat and minerals replace sunlight entirely, and where the deep's final form of life begins to reveal its origins in the very bones of the earth. Below the feeding grounds of the trench lies a quieter world still. The soft rain of organic matter fades, the movement of scavengers diminishes, and the sediment thickens into compact layers that smell faintly of sulfur and iron. Beneath these layers, the deep ocean begins to merge with the crust of the earth itself. It is a region defined not by sunlight or by the remnants of the surface, but by chemistry and heat, an intersection where geology and biology share the same vocabulary. It is here that the true factories of the abyss operate, unseen and tireless, driven by forces that began when the planet was still forming. The Kuril Trench is more than a deep scar in the seafloor. It's a boundary between two immense tectonic plates, the Pacific Plate sinking beneath the Okhotsk Plate. The motion between them produces friction, earthquakes, and heat. At depths of several kilometers below the seafloor, fluids trapped in the crust are heated and released upward through cracks. These hydrothermal seeps and vent-like systems are rare in the trench environment, but where they occur, they create pockets of extraordinary activity. They are the power plants of the abyss, converting raw geology into living energy. When these fluids rise, they carry with them dissolved metals, sulfides, and gases like methane and hydrogen. As they mix with the cold, oxygenated seawater above, chemical reactions occur. Metals precipitate out as mineral particles, and gases are oxidized by microbes that use them as fuel. This process, chemosynthesis, forms the foundation of ecosystems that exist entirely without sunlight. Instead of photosynthetic plants or algae, the base of the food chain here consists of bacteria that turn chemical energy into organic matter. They are the factories, the producers, the architects of an invisible economy that powers the deep. At first glance, these microbial mats seem lifeless, just pale films coating rocks or soft, filamentous layers spread across sediment. But under a microscope, they are vast, thriving communities. Individual cells cluster together, forming biofilms that behave almost like multicellular organisms. Within them, different species specialize in different reactions. Some oxidize hydrogen sulfide, others reduce nitrate, others fix carbon dioxide into sugars. The result is a self-sustaining system, each metabolic pathway feeding into the next. Where one microbe produces waste, another consumes it. Every reaction is linked. Every molecule is used. In areas of active seepage, the results can be dramatic. White bacterial mats cover the sediment, shimmering faintly under submersible lights. Small clams and mussels cluster nearby, living symbiotically with chemosynthetic bacteria inside their tissues. These animals no longer feed in the traditional sense. They rely on their bacterial partners to produce nutrients directly from the surrounding chemistry. The relationship is so complete that some species have lost their digestive systems entirely. They are living containers for bacteria, dependent on their partners but protected in return. This arrangement is efficient, elegant, and stable, a biological reaction chamber fueled by the heat of the earth. Nearby, tube worms grow in slow clusters, anchored to the rocks. They too depend on the internal bacteria. The worms absorb hydrogen sulfide and oxygen through their skin and deliver it to the microbes living inside a specialized organ. The bacteria use these compounds to produce sugars, which feed the host. The worm, in turn, provides structure and access to the fluids. It's an exchange without waste, a collaboration so refined that neither partner could survive alone. The factories of the abyss operate on trust built over millions of years. The chemistry that drives them is subtle. Hydrogen sulfide reacts with oxygen to produce water and sulfate, releasing energy in the process. Methane oxidizes to carbon dioxide. Hydrogen combines with carbon dioxide to form methane again. These cycles repeat endlessly, like gears turning within the planet. The balance between them defines the trench's chemical landscape. Small variations, changes in temperature, pressure, or mineral content can shift the entire system. Some seeps are dominated by sulfur bacteria, others by methane oxidizers. The ecosystem reorganizes itself accordingly, always finding equilibrium. At greater depths below the seafloor, life becomes even more minimal. Microbes living hundreds of meters beneath the trench sediments survive on trace amounts of chemical energy diffusing upward from the crust. They divide perhaps once a century, metabolizing so slowly that they seem frozen in time. Yet they are alive, capable of repair, adaptation and growth when conditions change. DNA extracted from these sediments shows extraordinary diversity. Some sequences are unique to the deep biosphere, unrelated to any known surface organism. Others resemble ancient lineages that may date back billions of years. The subsurface biosphere is vast, stretching through cracks and pores, an invisible network connecting the ocean to the mantle. This buried life influences global chemistry in ways scientists are only beginning to understand. By mediating reactions between rock and water, these microbes control the flux of carbon, sulfur and nitrogen between Earth's crust and its oceans. They act as regulators, maintaining the balance of gases that shape the planet's climate. The trench, with its enormous surface area and constant tectonic activity, is one of the key gateways in that exchange. What happens here, far below the surface, ripples outward across the entire biosphere. To grasp the scale of this hidden world, imagine that beneath every square metre of seafloor lies a living membrane of microbial life, extending down for kilometres. Each layer represents a different balance of chemistry. Near the surface, oxygen is still available, supporting aerobic respiration. Deeper down, oxygen disappears, replaced by nitrate, then sulfate, then carbon dioxide as electron acceptors. Each step downward changes the dominant community. The boundary between these layers is not sharp but gradual, a continuous transition of metabolisms. Together they form one of the largest ecosystems on Earth, one that may outweigh all surface animals combined. The heat driving these processes is ancient. It comes from the slow decay of radioactive elements in the Earth's interior and from the friction of tectonic motion. In the Kuril Trench, where one plate dives beneath another, this heat escapes unevenly, creating localized zones of activity. The seeps and vents that result are not dramatic geysers like those at mid-ocean ridges, but slow, diffuse leaks, trickles of warmth and chemistry sustained over centuries. They're quieter, subtler, but no less important. Over time, they shape the trench's ecology, feeding microbial networks that extend far beyond the visible seep. Occasionally, these chemical factories leave physical traces. Layers of carbonate and sulfide minerals precipitate from the fluids, forming crusts and chimneys. Within these structures, microbial fossils can be preserved, microscopic filaments and cells encased in mineral. When scientists collect and analyze them, they find evidence of metabolic reactions frozen in stone. The structures record a history of life intertwined with geology, showing how microbes influence mineral formation and vice versa. The boundary between living and non-living becomes blurred. The deep doesn't distinguish between biology and chemistry. It treats them as the same process. The reactions taking place here are slow but relentless. Hydrogen sulfide produced by decomposition above diffuses downward, where it reacts with metals and is oxidized by microbes. Carbon dioxide from seawater reacts with minerals to form bicarbonate. Methane rises from deeper layers, sometimes forming gas hydrates, solid crystals of methane and water that remain stable under high pressure and low temperature. These hydrates can trap enormous amounts of carbon. When disturbed by earthquakes or temperature changes, they can release methane back into the water, fueling new microbial blooms. The system is cyclical, interdependent and vast. For scientists, these processes are more than a curiosity. They're clues to how life might exist elsewhere. The conditions in the trench resemble those believed to exist on icy moons like Europa or Enceladus, where liquid water interacts with a rocky core beneath an icy crust. If life thrives here without sunlight, using only chemistry and heat, then it could thrive there too. The microbes of the Kuril Trench are not just survivors of Earth's extremes. They are ambassadors for the possibility of life beyond. Studying them, however, is difficult. Samples must be collected without contamination and kept under high pressure. Even small changes in temperature can alter their metabolism. Despite these challenges, researchers have managed to culture a few species in laboratory conditions that mimic the deep. These experiments have revealed enzymes that function under pressures hundreds of times greater than those at the surface. Some of these enzymes are now used in biotechnology, offering stable reactions in industrial settings. What evolved to survive the abyss now serves human ingenuity. The factories of the trench are, in a way, teaching us new chemistry. The energy efficiency of these microbes is astounding. Some species survive on less energy than the theoretical minimum for life. Their metabolisms operate so close to equilibrium that there's almost no waste. They exist on the edge of physics, converting minuscule gradients of energy into motion and growth. In doing so, they redefine what it means to be alive. The trench doesn't host life as we know it. It hosts life as matter rearranging itself to persist under constraint. It's an insight that reaches beyond biology into philosophy. Every reaction down here, every molecule processed, contributes to the grand cycle of elements. Carbon fixed by microbes eventually becomes organic matter. Sulfur oxidized into sulfate drifts upward, influencing ocean chemistry. Iron and manganese precipitate into nodules, storing trace elements for future epochs. The trench acts as both sink and source, a fulcrum balancing the planet's geochemical scales. The heat and chemistry of the abyss are not separate from the rest of Earth. They are its foundation. In the broader context of evolution, these chemical systems may represent the original blueprint for life. Before photosynthesis, before DNA, before complex cells, there were chemical gradients at the boundaries of rock and water. In those gradients, simple molecules assembled, reacted, and replicated. The factories of the abyss are echoes of that beginning, still running billions of years later. They are living fossils, not in form but in function, maintaining the processes that once gave birth to all life. When we look at them, we are seeing not the strange edge of biology, but its starting point. The Kuril Trench, though remote and forbidding, is a living archive of these origins. Each seep, each vent, each microbial mat is a page in the story of how the Earth maintains itself. The chemistry happening here connects to the chemistry in our own cells. The ATP that powers our muscles is made through reactions that mirror those used by chemosynthetic microbes. We carry the deep within us. The factories of the abyss are our distant ancestors still at work. Even the sounds of this world reflect its function. The low-frequency hum of tectonic motion, the faint crackle of gas bubbles rising through sediment, the periodic release of methane from hydrate layers. These are the rhythms of the deep's metabolism. If one could listen long enough, those sounds would form a continuous pattern, the heartbeat of a planet digesting itself in slow motion. It's not noise, it's the sound of equilibrium. As the submersible glides past one of these seeps, the water shimmers with refracted light. The camera captures threads of bacteria waving gently, clusters of clams half buried in sediment, and tiny particles of mineral drifting upward. It's an industrial scene without machines, production without noise. Every molecule of gas rising from the crust is transformed before it can escape. Every atom of carbon finds a use. The efficiency is absolute. The Earth wastes nothing. And yet, as we drift further along the trench floor, the heat fades again. The chemical gradients smooth out, the microbial mats thin, and the environment returns to stillness. The factories continue below, invisible, but at the surface of the sediment, life becomes sparse. The transition is gradual, not abrupt. The energy that drives the deep must pass through many filters before it disappears completely. In that slow fading lies the next stage of the journey, the point where knowledge meets ignorance, where discovery turns to speculation, and where we begin to ask what might remain hidden still deeper below. Because below even this layer of heat and chemistry, there are mysteries we haven't reached. Currents of life existing entirely within the rock, microbes that never contact seawater, forms of existence that challenge every definition we use. The factories of the abyss are not the end, they are the threshold, and beyond them, the unknown continues, still working, still transforming, still alive in ways we haven't yet learned to detect. For more than half a century, humans have tried to understand what lies at the deepest edges of the ocean. The Kuril Trench is not the most famous, not as widely known as the Mariana, but its isolation has preserved something unique. The technology that reaches these depths has improved, but each expedition still brings more questions than answers. What we have found so far is remarkable enough. A complete ecosystem operating beyond sunlight, built on chemistry and pressure, a world functioning on its own terms. Yet even with cameras, sensors and samples, what we know feels like a surface reflection of something still vast and unseen. The first clear glimpse came in the latter half of the 20th century, when Japan and Russia sent deep-diving submersibles to explore the Kuril-Kamchatka region. The images returned were dim and grainy, yet they showed unmistakable signs of life. Fish gliding close to the sediment, amphipods scuttling across camera frames, plumes of disturbed sand settling in slow motion. Later, baited cameras revealed a pattern. Certain creatures always appeared first, others followed hours later, and some never appeared at all unless the lights were off. Each new descent rewrote what scientists thought possible. Today, remote-operated vehicles and autonomous landers can reach nearly 10,000 meters. They carry instruments that detect temperature, salinity, dissolved gases, and chemical gradients. They record light levels so low they seem like numbers close to zero, yet even those faint photons are meaningful. In the Kuril Trench, sensors have measured periodic changes in water chemistry, fluctuations that suggest subtle biological activity continuing between visits. That pattern hints at a world not static but breathing in cycles, as though the trench itself were alive, pulsing slowly through its routines. Samples retrieved from the deepest sediments have revealed microbial diversity beyond imagination. DNA sequencing shows entire branches of life that don't fit into known classifications. Some microbes metabolize substances no surface organism could tolerate: arsenic, hydrogen, heavy metals, using them as energy sources. Others exist in symbiotic webs, exchanging compounds so specialized that removing one species can collapse the entire microcommunity. These findings have expanded biology itself. The tree of life has grown new branches because of them. Among multicellular life, discoveries are just as extraordinary. The Hadal snailfish, now emblematic of the trench's resilience, was once thought to represent the absolute limit of vertebrate endurance. But even deeper specimens have been observed, suggesting the limit might lie further still. Amphipods collected from the trench possess unique genetic adaptations for producing pressure-resistant proteins. Their enzymes remain stable at pressures that destroy human-made materials. Some researchers are experimenting with synthetic versions of these molecules for use in medicine and technology, exploring how nature's chemistry can strengthen ours. Each discovery carries implications beyond the immediate. When we understand how an enzyme functions under extreme pressure, we learn something about molecular structure that can apply anywhere, from drug design to industrial engineering. When we observe how an organism maintains cell integrity in freezing, oxygen-poor conditions, we gain insight into how early life might have survived Earth's ancient oceans. The Kuril Trench is not just a destination of exploration, it's a reference library for biology, chemistry and evolution. Still, for every pattern we recognize, there are others that remain hidden. Many camera deployments record movements in the background, shadows too faint or distant to identify. Sometimes the sediment shifts where no visible animal is present. Sometimes the instruments detect vibrations with no known source. The deep doesn't reveal itself completely, and perhaps it never will. What hides there is not necessarily monstrous or alien. It may simply be delicate, adapted to move in ways we can't perceive, existing in chemical niches that our instruments can't yet measure. Part of the challenge is that the trench is a moving system. The tectonic activity that shapes it also constantly reshapes its walls and floor. Landslides can bury entire communities, while new vents can open within days. A camera left for months may return to find the landscape completely altered. The deep is not static. It is dynamic at geological speed. Life here has evolved to adapt to those shifts, but our observations, brief as they are, capture only fragments of that motion. There are also physical limitations. Light cannot travel far through these depths, and artificial lighting can alter behaviour. Sound, while effective for mapping, can disturb sensitive species. Every method of observation risks changing the very thing being studied. The deeper we look, the more we realise how intrusive our presence is. For now, much of what remains hidden stays that way, because it must, because the act of seeing disturbs the balance that allows it to exist. Yet even indirect signs tell stories. Traces of genetic material, environmental DNA, drifting through water samples reveal unseen inhabitants. By analysing those fragments, scientists can identify species that have never been captured or filmed. In the Kuril Trench, eDNA surveys have found sequences belonging to unknown fish, crustaceans and microorganisms. Some match known relatives from other trenches, others appear entirely new. It's a quiet form of discovery. No image, no specimen, just a molecular footprint left behind. Still, it expands our understanding of what's down there. The discoveries also carry reminders of how fragile this world is. When sediment cores are brought to the surface, they reveal layers of microplastics, chemical pollutants, and radioactive isotopes that trace back to human activity. These materials have travelled thousands of kilometres, carried by currents that connect the shallowest waters to the deepest trenches. Even here, far removed from the surface, our presence is felt. Amphipods have been found with synthetic fibres in their digestive systems. Bacteria have begun colonising plastic fragments as if they were natural rock. The deep adapts, but adaptation doesn't mean immunity. What we find and what we leave behind are now part of the same story. The mystery isn't only biological. The geology of the trench holds puzzles too. Magnetic anomalies detected near the subduction zone suggest movements of fluid and molten material far below the seafloor. Those fluids might carry minerals that feed chemosynthetic ecosystems, or they might alter the chemistry of the ocean over millennia. Each discovery of heat flow, each anomaly in gas composition, offers a clue to processes linking the biosphere and the geosphere. Understanding those connections is essential to grasping how Earth regulates itself. There is also the matter of sound. Hydrophones deployed for long durations continue to pick up unidentified low-frequency noises. Some correspond to distant earthquakes or landslides. Others don't fit any known pattern. A few signals repeat at regular intervals, changing with the seasons. Some scientists suggest they could be biological, perhaps large animals communicating across vast distances, but there is no confirmation. In the silence of the deep, every unexplained sound feels like an invitation to imagine. The question of what still hides there isn't one of monsters or secrets, it's about scale and perception. The trench spans hundreds of kilometres, its floor fractured and folded into ridges and basins. Each depression, each slope, could host a distinct ecosystem. To explore it fully would take lifetimes. Even our most advanced robots can cover only a small fraction each year. For every square metre we have filmed, millions remain untouched. If there are unknown forms of life, they could exist anywhere within that expanse, perfectly content in their isolation. Some scientists believe entire ecosystems remain undiscovered within the subsea floor, where fluids circulate through pores and fractures. In these spaces, microbes may live completely cut off from the open ocean, sustained only by minerals and heat from below. Their chemistry could differ so completely from surface life that they represent a parallel biosphere. Samples taken from deep boreholes hint at this possibility. Microbial cells found kilometres below the seafloor, surviving in total darkness with almost no energy input. These cells blur the boundary between life and non-life, existing in a state of near-suspended animation, waiting centuries between metabolic reactions. If such forms exist beneath the Kuril Trench, they would be part of the planet's hidden majority. By some estimates, the total biomass of subsurface microbes exceeds all animal life combined. They may influence global chemistry in ways we don't yet detect, slowly altering the composition of the ocean from within. Their presence suggests that the deep isn't just a refuge for life, it's one of its central engines. The trench, then, is not the end of the biosphere, it's its core. Still, for all our progress, the gaps in knowledge are immense. Each new expedition raises as many questions as it answers. How do these communities evolve in isolation? How do species disperse between trenches separated by thousands of kilometers? What controls their population cycles? Even basic measurements, growth rates, reproduction, feeding behavior remain incomplete. Decades of research have given us glimpses, not portraits. And there are the questions that go beyond biology. What does it mean for a planet to host life so deep that it never interacts with sunlight? What does it reveal about the resilience of matter itself, about the way complexity arises from constraint? These are questions without simple answers, but they are the ones that make the Kuril Trench more than a geological feature. It is a philosophy written in rock and pressure, a demonstration that life doesn't occupy the world, it integrates with it. Every new discovery reinforces that idea. The microbes that oxidize methane at seeps regulate global greenhouse gases. The amphipods that recycle carcasses keep the ocean's chemistry balanced. The slow burial of organic matter locks carbon away for eons. Each small, unseen process contributes to planetary stability. The trench may look remote, but it's connected to every breath on land. The deep's metabolism sustains the surface. Even our limitations in studying it teach humility. When researchers recover a sample from 8,000 or 9,000 meters, it takes years to analyze properly. Each cell, each molecule, each trace of isotope becomes part of a vast puzzle. It's not just data, it's evidence that the Earth is still more alive than we know. The hidden world beneath the Kuril Trench challenges every assumption of scale. What counts as life? What counts as energy? What counts as discovery? In that sense, what we've found is less important than what remains beyond reach. The unknown isn't a void, it's the continuation of everything we already see. The deep is not withholding its secrets, it's simply operating at a pace and scale that we're not built to perceive. Our understanding of it expands as slowly as its own metabolism. Each question answered opens 10 more. Yet the persistence of mystery isn't failure, it's what keeps exploration alive. The more we learn about the trench, the clearer it becomes that its greatest contribution is perspective. It shows that life can thrive where physics should prevent it, that ecosystems can exist without light, and that the line between chemistry and biology is thinner than we thought. It reminds us that the planet's story is not written on the surface, but in layers descending into silence. And so, the Kuril Trench remains both a discovery and a frontier. We have found its creatures, its chemistry, its rhythms of decay and renewal. But we have not yet touched its deepest layers, the hidden networks that bind it to the Earth's core. The journey downward continues, each expedition another sentence in a story still unfolding. And as the machines rise again toward the surface, their lights dimming behind layers of pressure and darkness, the world they leave continues undisturbed. The unseen remains unseen, the quiet undisturbed, the hidden still patiently working. What we've found is remarkable. What we haven't is inexhaustible. Beneath that unbroken stillness, something continues to move, slowly, invisibly, shaping the chemistry of the ocean and the balance of the world above. To follow it further means letting go of what we think life must look like, and instead recognizing it in the smallest exchanges of energy and matter. Below the known lies what still hides, not waiting to be discovered but simply existing as it always has. And as we drift along the bottom of this thought, it's time to notice how the silence itself begins to deepen again, how sound and motion fall away until there is only stillness left. It's not the end of the story, just another descent. into a place where the quiet becomes its own kind of presence, where the deep stops resembling a place and begins to feel like an idea. That's where we continue next, into that stillness, into the space where even observation ends and only reflection remains, the final layer of the descent where the deep watches back. The trench doesn't end where we think it does. The measurements might show a floor, a number written in meters, but the experience of it doesn't stop there. When light, motion, and even sound begin to fade, the space takes on another quality, something less physical, more perceptual. The instruments register almost nothing, but that absence isn't empty. The water is still moving, molecules still colliding, chemistry still unfolding in its slow rhythm. What remains is an awareness of everything continuing without us, a stillness that isn't silence but balance. When the cameras shut off and the last sonar pulse fades, what lingers is the sense that the deep is watching. Not in a conscious way, not with lies or intention, but with presence. The Kuril Trench, like every deep place on Earth, reflects the sum of all that has passed above it. It carries the record of falling things, dust, cells, bones, and history, layered so thickly that time itself seems trapped within it. If you could read the sediment like a book, you'd find pages written in chemical ink, each one telling what the planet was doing when it fell. Volcanoes, extinctions, migrations, storms, they all leave traces here, compressed and preserved. The stillness isn't a pause, it's the archive of movement. To call it stillness is almost misleading. The deep never stops. Even in its quietest layers, water flows in microscopic currents. Heat moves upward from the crust. Microbes divide once in a century. Carbon shifts from one form to another. The absence of motion is only relative to our impatience. If we could stretch our perception to the pace of the abyss, we would see constant activity, just measured differently, slower, more deliberate. Every chemical bond breaking and reforming, every particle settling, every ripple of energy absorbed by pressure, that's what this stillness contains. It's the motion of things that have learned how not to hurry. The submersible lights reveal nothing now but suspended particles. They drift like dust in a vast room, spiraling and rising and falling again. They are fragments of what was alive once, or perhaps what will be again. The line between the two is impossible to draw. At these depths, the distinction between living and not living dissolves. Minerals precipitate around bacterial cells, and bacterial cells feed on minerals. The process blurs into a continuum. To call one life and the other matter stops making sense. Everything is both, constantly shifting state. It's in that blurring that reflection begins. When we think about the deep, we tend to imagine it as alien, detached from the rest of the world. But the trench isn't an elsewhere, it's the foundation. Every cycle that sustains life above depends on what happens here. The carbon buried in sediment, the oxygen balanced by microbes, the minerals redistributed through slow convection, all of it feeds back into the surface. The stillness below is what allows the surface to move. Without the deep's patience, the atmosphere would collapse into chaos. The oceans would choke on their own nutrients. The balance that makes life possible exists because somewhere far below there is restraint, and that restraint feels conscious even though it isn't. It's the quiet intelligence of the planet, the sum of physical laws that have reached harmony through time. The deep doesn't choose to be calm. It is calm because it has already found equilibrium. It's not a question of adaptation anymore, but of existence perfected. Down here, everything that could happen has already been tested. Every molecule that could bond has bonded. What remains is endurance. The stillness also reveals something about how small we are. Our presence at the surface, our noise, our structures, our speed barely touches this place. Even when our plastic and waste fall to the bottom, they become absorbed into the system, colonized, digested, redefined as part of it. The deep doesn't reject anything, it transforms it. Time erases the signature. A thread of synthetic fibre becomes substrate for bacteria. A shard of glass becomes mineral. An iron particle from a shipwreck becomes part of a nodule. The trench accepts everything and waits long enough for it to make sense. Scientists often describe this waiting as stability, but it's more than that. It's the absence of urgency, a kind of timelessness that doesn't oppose change but absorbs it. If you could measure time here, it would flow like cold syrup, slow, viscous, yet unstoppable. A microbe's lifetime might span a millennium. A chemical cycle might take 10,000 years. Even tectonic movement, which reshapes continents, feels unhurried when measured against this background. The stillness is not static. It's infinite motion slowed to the limit of perception. When researchers recover sediment cores from the trench, what they hold in their hands is history in physical form. The upper layers contain remnants of modern ocean life. Below that lie ancient layers, compacted until they resemble stone. Each centimetre represents decades or centuries. Embedded within are microfossils, chemical residues, isotopic ratios that trace the evolution of Earth's climate. The deep records everything but without commentary. It's the most objective observer imaginable, indifferent, consistent, complete. The stillness watches by collecting. Every observation we make of the trench changes us more than it changes it. To see something function so efficiently, so continuously, forces us to reconsider our definitions of complexity and intelligence. The deep operates without oversight or planning, yet its cycles are flawless. It maintains balance through feedback built into the physics of matter. There's no leader, no center, no design, and yet it endures. In that endurance lies a kind of wisdom that biology inherited but rarely imitates. The reflection that emerges from this isn't philosophical for its own sake, it's practical. The systems we build on land often fail because they chase stability without patience. The trench achieves stability through slowness, through distributed adaptation, through the absence of hierarchy. If one part collapses, another absorbs the loss. If energy falters, the system waits. The lesson isn't mystical, it's mathematical. Sustainability isn't achieved through control, but through time. The Earth learned that long before we arrived. In the silence of the deep, those lessons feel immediate. When you imagine yourself down there, no sound, no light, no surface, you begin to understand how little life needs to continue. It doesn't require direction, only conditions. Heat, pressure, water, time, that's enough. The rest is negotiation between molecules. The longer you think about that, the more comforting it becomes. Life is not fragile, it's relentless. Even if everything we built on the surface disappeared, the processes in the trench would continue unchanged. The planet would keep breathing through its deep lungs. The stillness of the trench can also be read as reflection in a literal sense. Acoustic waves sent into it bounce back, carrying information about the shape of its walls and the layers below. Those echoes, when translated into data, create maps of what lies unseen. The patterns look abstract at first, lines and gradients, but they're the trench's way of answering. We send sound, it returns with structure. Every echo is a conversation across pressure and depth, the planet responding in the only language it knows. There's something humbling in that exchange. The deeper we listen, the quieter the answers become, until what returns is almost nothing at all. The stillness doesn't resist our questions, it absorbs them. It doesn't need to explain. Its existence is explanation enough. When we call the deep alien, what we're really saying is that it doesn't resemble us. But in reality, it's the baseline, the norm, the state from which we're the deviation. The stillness watches back by showing us what constancy looks like. And yet, even this constancy isn't eternal. Over geological time, trenches migrate, fill, and vanish. The Kuril Trench itself will eventually close as the Pacific Plate continues to descend, melting into the mantle. The sediments and life forms it holds will be drawn downward, recycled into magma, and someday return to the surface as volcanic rock. The stillness is part of that cycle too. It's not a permanent rest, but a stage in transformation. What seems like eternity is only duration on a different scale. To the planet, 1,000,000 years is a breath. That perspective changes how we see ourselves. We tend to think of deep time as something distant, abstract. But every breath, every step, every drop of water we drink connects to these slow processes. The oxygen we breathe may have once been bound in minerals at the bottom of an ancient trench. The calcium in our bones might have come from shells crushed and buried in the abyss millions of years ago. We are built from recycled stillness, animated by the same chemistry that keeps the deep alive. The trench isn't below us, it's within us. To acknowledge that connection isn't to romanticize it, but to recognize responsibility. The stillness is tolerant. It absorbs our waste, our excess, our noise, but it isn't infinite. If too much change reaches it too quickly, the balance can shift. Temperature rises, oxygen declines, carbon accumulates. The deep responds slowly, but it does respond. Every action at the surface eventually finds its way here, written into the sediment. The stillness keeps records, and those records tell the truth. Scientists studying those records have already found signs of the Anthropocene in the abyss: microplastics, chemical residues, altered isotopic ratios. Our presence is there now, layered among natural history. Even if we disappeared tomorrow, that signature would remain for millions of years. It will tell future observers, if any exist, that there was once a species that reached every corner of the planet, even the ones it never saw. The deep doesn't judge, but it remembers. Still, even as it records, it continues to host life with perfect neutrality. The amphipods still feed, the microbes still divide, the sediment still breathe. The trench adapts because that's all it knows how to do. The stillness that watches isn't waiting for redemption or catastrophe. It's simply continuing. The reflection it offers is not moral but existential. It shows that endurance doesn't depend on perfection, only on participation in the cycle. Everything that falls becomes part of it eventually. If you could sit here long enough, you would feel that patience as a kind of presence, not mystical but physical. The weight of water pressing from above, the cold that never changes, the faint vibration of the planet's motion beneath you. It's a reminder that the Earth is never truly silent. Its pulse is just slower than ours. The stillness is a form of sound stretched across time, a resonance so long that we mistake it for quiet. What the trench teaches finally is that to exist is to be part of this ongoing process. Life doesn't conquer the deep, it completes it. Every adaptation, every metabolism, every death and renewal fits into the larger pattern. The stillness that watches back isn't passive, it's interactive. It shapes what survives by offering the conditions under which only certain things can endure. It's selective through physics, not intent. And through that selection, it maintains the continuity of the planet. When the submersible begins its ascent, leaving the trench behind, nothing in the abyss changes because of it. The lights fade, the machinery hums upward, and below the stillness continues exactly as before. The amphipods return to feeding, the bacteria resume their cycles, and the sediment keeps accumulating. The deep doesn't need witnesses to exist. It is self-sufficient, self-explanatory. The act of observing it adds nothing to it but much to us. And so the reflection turns inward. The stillness that watches back is also the stillness within, the part of human thought that slows when confronted with scale too vast to measure. It's the same quiet that exists between heartbeats, between breaths, between thoughts. To sense the deep is to experience that stillness, to realize that what feels alien is actually the planet's most natural state. The abyss isn't a mirror of emptiness, it's a mirror of balance. The Kuril Trench, in all its depth and patience, shows that the universe doesn't require light or sound to be alive. It needs only time and matter arranged in such a way that energy can flow. Everything else, colour, voice, meaning, is temporary. The stillness is what remains when the noise is gone. It isn't the end. It's the background that allows beginnings to happen. And as we surface again into light, carrying data, samples and questions, that realization lingers. The deep continues beneath, unseen but ever present, a constant awareness beneath the restless skin of the world. It doesn't fade or sleep. It endures, unbothered, unchanging in its purpose. It's not waiting to be known. It already knows.